Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. We speak of everything, yet we hardly grasp its magnitude. Everything is the totality of existence, the stars and galaxies, time and space, energy and matter, life and mind. It is all that is, all that ever was, all that ever will be. In its embrace are the quiet dust under our feet and the shining furnaces of distant suns, the hum of a thought and the roar of a supernova. To contemplate everything at once is to stand at the shore of an infinite ocean, awed and humbled. Even our most fleeting reflection on the cosmos can send a shiver down the spine, as if some deep part of us remembers that we are a part of this grand tapestry, woven into its very fabric. On a clear night, under a vault of stars, we gaze upward and attempt to fathom our place in a vastness without obvious bounds. We see pinpoints of light scattered across a canvas of darkness, each a sun, perhaps with its own planets and stories. We feel small, yet we are connected to all of it. The iron in our blood, the calcium in our bones, the carbon in our DNA, these were forged in the hearts of ancient stars. We are children of the cosmos, built of its matter, energized by its light, and guided by our curiosity to understand it. Through science and imagination, we stretch our minds toward the edges of the universe, seeking to grasp how all of this came to be. From time immemorial, we have gazed at the heavens and spun stories about our place among the stars. Today, our tools are telescopes and equations, but the sense of wonder remains as profound as ever. In this journey, we will blend science and poetry, fact and metaphor, as we explore the cosmos on every scale. We will touch on cosmology and physics, astronomy and mathematics, philosophy and human curiosity, all the lenses through which we seek understanding. Together, let us venture to the very beginning of time and back, and to the farthest reaches of space, in pursuit of the story of everything. Our journey begins at the very beginning, at the origin of everything we know. In the primordial darkness, before a single star had ever shone, all that would become the universe was cradled in a point smaller than an atom. It is nearly impossible to imagine. A seed of unimaginable density and heat, a single point that held the potential for galaxies, for life, for every atom and every moment in time. And then, in an instant about 13.8 billion years ago, that seed exploded into growth. There was a flash of pure creation, a moment we call the Big Bang. Time and space themselves were born in that moment. What had been nowhere became everywhere. What had been nothing became everything. The newborn universe expanded with incomprehensible fury. In a tiny fraction of a second, it swelled from microscopic to cosmic scales. This extraordinary growth spurt, known as cosmic inflation, stretched space like a balloon inflating at faster than light speed. Distances between points grew by an enormous factor, smoothing out any clumps or curves. Inflation explains why the universe today is so uniform and flat on large scales. It was as if any initial wrinkles in space were ironed out by this tremendous expansion. A smooth, seething fireball emerged from that initial burst. Tiny quantum fluctuations, random little flickers of density in that early vacuum, were blown up by inflation into slight variations in the otherwise even spread of matter. These faint imprints would one day guide the formation of galaxies, but for the moment, the infant universe was a hot, dense soup of energy. As inflation settled, the energy driving it transformed into matter and light. The universe was 1 second old. In that first second, space was filled with an intense, blinding glow, radiation so hot that it would have vaporized anything, though as yet, there was nothing but fundamental particles. Matter and energy were not yet distinct. They flowed together in a plasma, a fluid of raw creation. Protons and neutrons jostled in temperatures of billions of degrees. In the minutes that followed, the entire universe itself became a nuclear reactor. These building blocks began to combine in countless tiny nuclear forges across the young cosmos. Protons fused with protons, neutrons linked with protons. By 5 minutes of cosmic time, the first atomic nuclei had formed. The simplest elements came into being: hydrogen, the lightest of all, and helium, its slightly heavier kin. A trace of lithium also appeared. In that brief early epoch of nucleosynthesis, the universe forged the basic chemical foundation it would use to build everything else. About 3/4 became hydrogen and 1/4 helium by mass, an elemental newborn universe. Still, no atoms as we know them could yet exist. The universe was far too hot for electrons to settle into orbits around nuclei. Instead, electrons careened freely through the dense plasma, scattering light incessantly. Photons, the particles of light, were trapped in a cosmic fog, bouncing from one free electron to another. Space glowed as bright as the interior of a star, but no light could travel far. The universe was opaque, a brilliant radiance suffused within a swirling, glowing mist. As seconds turned to minutes, minutes to hours, and hours to years, the young cosmos continued to swell and cool. Hundreds of thousands of years passed. Expansion took its toll on the fireball, diluting and cooling it steadily. At around 380,000 years after the Big Bang, a critical threshold was crossed. The temperature fell enough that electrons could finally be captured by nuclei. Protons clutched electrons to form hydrogen atoms. Helium nuclei gathered electrons to become helium gas. This transition is called recombination, though it was the first time such combination had occurred. With electrons now bound into atoms, the fog lifted. The once captive light was free at last. In every direction, a brilliant afterglow burst forth and raced away through space. The universe that had been opaque became transparent. That first light still surrounds us today. It has cooled to a gentle microwave glow that bathes the entire sky. The cosmic microwave background, the oldest light we can see. Back then, it was a searing, orange-white illumination everywhere. As space expanded and cooled, that light's wavelength stretched beyond red, through infrared, and into the microwave part of the spectrum we detect today. Discovered as a faint hiss in radio antennas, this afterglow is a whisper from the time the universe took its first breath as a transparent cosmos. The universe then entered a deep, dark age. With the primal light released and streaming onward, space itself went dark. There were not yet any new sources of light. The primordial gases, mostly hydrogen and helium, now drifted through expanding space like a vast, invisible fog. Gravity, the great sculptor, began to gently tug on the ever-so-slight variations in density left by inflation. Regions that were just a bit denser than average exerted a stronger pull, drawing in matter from their surroundings. Invisible threads of gravity started weaving patterns in the darkness. Over tens of millions of years, those threads pulled gas into clumps. The silent clouds grew denser and tighter until, at last, there was fire again. Perhaps 100 million years after the Big Bang, the first stars were born. Deep in massive collapsing clouds of hydrogen and helium, the pressure and heat ignited nuclear fusion. Starlight pierced the darkness. These first stars were giants, short-lived behemoths burning hot and blue, forging heavier elements in their cores as they shone. They lived for only a few million years before dying in titanic supernova explosions, seeding the surrounding space with the new elements they had cooked up: carbon, oxygen, nitrogen, iron. Ingredients that one day would be essential for planets and life. The death of each star sent enrichment into space, and out of the ashes, new generations of stars would eventually form. Their brilliant ultraviolet light also gradually burned off the primordial hydrogen fog in intergalactic space, reionizing the cosmos and allowing light to travel freely everywhere. With the birth of stars, the cosmos had begun to light up structure by structure, ending the long night of the Dark Ages. The cosmic dawn gave way to a growing day as the first stars and nascent galaxies illuminated the heavens. As stars gathered, they formed the first proto-galaxies, small galactic building blocks that later merged into larger ones. Gravity continued its tireless work on grander scales. Stars bound themselves into galaxies, and galaxies gravitated into clusters. Over hundreds of millions, and then billions of years, a vast cosmic web took shape. Galaxies pulled on one another along filaments of invisible matter, collecting into chains and sheets. Imagine a spider's web made not of silk but of galaxies, strung along invisible filaments, with enormous voids of near-empty space in between. Astronomers mapping millions of galaxies, for instance in the Sloan Digital Sky Survey, have unveiled this vast cosmic web in detail, huge filaments like the Sloan Great Wall stretching across hundreds of millions of light-years, and immense voids nearly empty of galaxies. It serves as the large-scale structure of the universe. Galaxies grouped like sparkling dew on cosmic threads, clusters at their intersections, and between them, great dark gaps where few galaxies shine. Interestingly, researchers have even drawn analogies between the cosmic web and biological systems. One experiment showed that a slime mold, when presented with simulated galaxy clusters as nutrient sources, grew tendrils that closely traced the filaments of the cosmic web, as if nature repeats patterns on vastly different scales. From a vantage point far away, the universe would look foamy or spongy, matter gathered into fibrous clusters surrounding empty cavities. And within each galaxy, countless stars swirled, orbiting their galactic centers like bees around a hive. What about the universe as a whole? Is it shaped like a sphere, a saddle, a donut, or an infinite flat expanse? As far as we can discern, space on the largest scales is remarkably flat, like an endless plane. If you set off in a straight line among the galaxies, you would not curve back around to where you started, at least not within any distance we can observe. The cosmos could extend forever, infinite in extent. It might also be finite yet unbounded, curving back on itself only on scales beyond our observational reach, rather like the surface of a balloon is finite, yet has no edge. Current measurements of cosmic geometry show no significant curvature. To the best of our knowledge, parallel beams of light travel straight and never meet. It is currently unknown whether the universe might eventually loop back in some topologically complex way, like a 3D torus. But if it does so on a scale far larger than the observable horizon. In all directions, space stretches out similarly, giving us no hint of an edge or a boundary. We are, however, limited in what we can see, not by any solid wall at the universe's edge, but by time itself. The observable universe is a sphere around us, about 46 billion light-years in radius, delineated by the distance light has been able to travel since the Big Bang. We can only see as far as the light that has had time to reach us. Beyond that horizon, light from those regions has not yet arrived, and perhaps never will. Thus, we gaze out at a bubble of the universe around us. Beyond it, the mystery continues, perhaps with more galaxies and more cosmic web stretching indefinitely, or perhaps something radically different. For now, it remains hidden, a tantalizing unknown just out of reach. The cosmic horizon is not only a physical limit, it's also a reminder of our cosmic myopia. It's like standing on the shore of a vast ocean at night. We see the dark waters meet the sky at the horizon and wonder what lies beyond. Our cosmic horizon is such a shore, and though we cannot see past it, we imagine an endless sea beyond. Even as structures formed and stars lit up, the overall expansion of space never halted. The universe kept stretching, carrying galaxies farther apart from each other. The very fabric of space is like an ever-expanding canvas, and the galaxies are like dots of paint on that canvas, drifting away as the canvas grows. The light that travels between galaxies is stretched too. As space expands, wavelengths of light elongate, shifting toward the red end of the spectrum. Thus, when we observe distant galaxies, their light is reddened, a cosmological redshift that encodes their motion through the expanding space. In the early 20th century, astronomers armed with new telescopes made a profound discovery. Nearly all galaxies beyond our local group are racing away from us, and the farther they are, the faster they recede. Edwin Hubble measured this relationship, finding that the speed of recession is proportional to distance. Today, this rate of expansion, known as the Hubble constant, is roughly 70 kilometers per second per megaparsec, meaning a galaxy about 3.3 million light-years away recedes at roughly 70 kilometers, and one twice as far at about 140 kilometers. This linear relationship, now called Hubble's law, was revolutionary evidence that the universe is expanding uniformly in all directions. It is not that we are at the center of an explosion, but rather that space itself is swelling, so every galaxy sees others moving away. Imagine raisins in a rising loaf of bread. Each raisin sees the others receding as the dough between them expands. Just so, our Milky Way and all galaxies are like raisins embedded in the expanding space of the cosmos. Yet even as Hubble and others revealed an expanding universe, other observations soon uncovered a deeper mystery in those galaxies. In the later 20th century, astronomers like Vera Rubin noticed that stars at the outskirts of spiral galaxies were orbiting their galactic centers at startling speeds, too fast to be explained by the gravity of the visible stars and gas alone. According to Newtonian physics, those outer stars should have been flung off into space, or conversely, one would need far more mass in the galaxy to hold them in their orbits. Something unseen, some additional gravitating mass, was providing the extra pull. Similarly, clusters of galaxies were found to contain far more gravity than the visible matter could supply. It was as if an invisible halo of mass surrounded clusters and individual galaxies alike. This mystery substance was dubbed dark matter. It does not shine or interact with light, making it invisible and detectable only through its gravity. But it is abundant, far more abundant than the ordinary matter we see. Roughly 85% of the matter in the universe is dark matter, about 5 times more mass than in normal atoms. It acts as the scaffolding of the cosmic web. It clumps under gravity, forming massive halos, and ordinary gas falls into those halos to form galaxies. Without dark matter's guiding hand, the universe would lack much of the structure we observe. Galaxies might not have had enough gravitational glue to coalesce as they did. We even observe gravitational lensing, light from distant objects bending around invisible mass, revealing dark matter's presence. In colliding galaxy clusters like the Bullet cluster, the normal matter, hot gas visible in X-rays, can be seen to separate from where most of the gravity is. The gravitational center follows the unseen dark matter, providing direct evidence of this hidden mass. We still do not know what dark matter is. Perhaps some as yet undiscovered elementary particle that interacts only weakly with normal matter, often hypothesized as WIMPs or axions, or something more exotic like primordial black holes or a modification of gravity itself. Experiments deep underground and in particle accelerators are attempting to detect dark matter particles directly, so far without success. For now, we infer dark matter's presence by how it holds galaxies together and how it tugs on light passing by. It is the universe's invisible skeleton, a shadowy scaffolding that shaped the beautiful pattern of galaxies and clusters, all while remaining hidden from our eyes. As if dark matter were not mysterious enough, an even stranger ingredient dominates even that. For a long time, scientists assumed that the expansion of the universe, while continuing, should be slowing down over time. After all, gravity pulls all matter together. The collective gravity of galaxies, dark matter, gas, and stars should gradually tug at the expansion, perhaps even causing it to reverse in the far future. But in 1998, two teams of astronomers observing distant Type Ia supernovae, exploding stars used as standard candles, made a shocking discovery. The supernovae were dimmer and farther away than expected, indicating that the expansion of the universe was not slowing at all. It was speeding up. Over the last few billion years, the galaxies have been accelerating away from each other. Some kind of force or energy inherent to space is pushing them apart. Decades earlier, Albert Einstein had introduced a cosmological constant into his equations of general relativity to allow for a static universe, not realizing the universe actually expands. When Hubble's expansion came to light, Einstein reportedly called that constant his greatest blunder. But now, the accelerating cosmos implies something like Einstein's constant truly exists after all. We call this phenomenon dark energy, a name that signifies how little we truly understand it. Dark energy appears to be a property of space itself. Every cubic centimeter of vacuum seems to carry a minuscule amount of energy that, summed over billions of light years of emptiness, dominates the universe. Today, roughly 68% of the universe's total energy content is this dark energy, with about 27% dark matter and only 5% normal matter composing the rest. It behaves almost like an anti-gravity, driving galaxies apart on large scales and overpowering the attractive force of gravity at cosmological distances. Perhaps dark energy is a fixed property of the vacuum, a realization of Einstein's cosmological constant, or perhaps it changes over time, a dynamic field dubbed quintessence. Upcoming observatories and surveys are dedicated to measuring the expansion history more precisely, in hopes of discerning the true nature of this mysterious energy. For now, dark energy remains an enigma at the heart of cosmology, a gentle but inexorable push woven into the fabric of space-time. What does an accelerating expansion mean for the future? The fate of the universe hinges on dark energy's nature. If dark energy remains constant, a steady push that continues indefinitely, then the expansion will not only continue, but accelerate forever. Galaxies that are not gravitationally bound to us will recede faster and faster, eventually zooming away at such speeds that their light can no longer reach us. In tens of billions of years, distant galaxies will disappear beyond our horizon, leaving only the gravity-bound local group of galaxies, by then likely merged into one large galaxy, visible. If we look far, we'll see darkness where once galaxies twinkled. Over extremely long timescales, the stars within our remaining galaxy, or merged Milk-Dromedar galaxy, will age and die. New stars will form more slowly as the available gas becomes sparse. Trillions of years from now, the last stars will exhaust their fuel and flicker out one by one, leaving a universe populated only by faint stellar remnants, white dwarfs cooling to black, neutron stars, and black holes. The cosmos will grow colder and darker as eons pass. Eventually, even black holes will evaporate via Hawking radiation, on timescales so vast, 100 years or more, that they defy imagination. What remains will be a thin haze of fundamental particles and energy, spread so dilute that for any given volume of space, on average, there might be essentially nothing in it. This is the Big Freeze or heat death scenario, a universe that expands forever while cooling asymptotically toward absolute zero, approaching a state of maximum entropy where no organized energy remains to do work. If an astronomer were alive in that far future of a Big Freeze, they would see a very different sky. Beyond our small gravitational neighborhood, no galaxies would be visible at all, only an endless black void punctuated by the occasional faint glow of a red dwarf or the spark of a distant supernova, becoming rarer with time. The evidence of the Big Bang itself would fade. The cosmic microwave background, which today is a cool 2.7 K glow, would be stretched to radio waves so long and weak as to be undetectable, The chemical elements would slowly transmute as protons perhaps decay over immensely long times, if proton decay is a real phenomenon. Eventually, it would be a universe of scattered particles and low-energy photons, drifting in an ever-growing silent darkness. Time would continue, but virtually nothing of interest would happen. It is a state as close to true cosmic stillness as can be. The universe would have effectively died, not with a bang, but with a long, drawn-out whimper. There are even more violent speculative possibilities. If dark energy is not constant but instead grows stronger with time, imagine a form of phantom energy, then the acceleration would steepen catastrophically in the far future. In such a scenario, the repulsive effect of dark energy could increase without bound. One could imagine the final moments of such a universe. Galaxies rush away from each other at ever-increasing speeds. Eventually, in the distant future, the expansion's pull becomes so strong that it overcomes the gravity holding galaxies together. First, galaxy clusters are pried apart. Later, the galaxies themselves begin to fly apart as their stars disperse into the expanding void. Then solar systems destabilize, planets drift away from their stars. As the end approaches, even stars and planets themselves would be torn apart, and then molecules and atoms. In the last fractions of a second, the tidal forces of expansion would become essentially infinite, shredding the very subatomic particles. This hypothetical final calamity is called the Big Rip. It would be a universe ending in a kind of ever-accelerating explosion, where every bond, gravitational, electromagnetic, even nuclear, is overcome by the expansion of space. One moment, you might have galaxies. Moments later, only individual atoms. Finally, nothing at all but a thin, featureless energy as space rips itself apart. It's a highly speculative scenario. Current data do not favor such extreme dark energy behavior, but it serves to illustrate the dramatic ways our universe's story could conclude under different rules. On the other hand, what if dark energy were to weaken over time, or even reverse sign? Or what if the universe had contained so much matter that gravity could eventually overwhelm expansion? In those cases, the expansion might slow down, stop, and ultimately reverse. Distant galaxies that are now receding would one day halt and begin to come closer again. This is the Big Crunch scenario, the opposite of the Big Bang. In a universe headed for a big crunch, observers in the far future might see the expansion first slow to a crawl. Distant galaxies that once sped away would linger at the edge of visibility. Then, gradually, they would start to approach, their light shifting from red back to blue. The cosmos would begin to shrink. Over billions of years, separated clusters of galaxies would converge. Previously unreachable galaxies would become visible again as they rush inward. The cosmic microwave background temperature, which had been dropping, would begin to rise as the universe contracts and heats up. Eventually, the night sky would no longer be dark, but aglow, first dotted with an increasing number of bright galaxies coming together, then suffused with the glow of a background fire as intergalactic gas is compressed and reheated. In the final epoch, the entire sky might blaze like the surface of a star, white hot, as galaxies merge into a single, incandescent mass. Finally, all matter and energy would crash together in an ultra-dense state, perhaps a mirror image of the Big Bang. Some have imagined that such a collapse could bounce, an implosion leading to a new explosion, a Big Bang after the Big Crunch, giving birth to a new universe. This Big Bounce idea suggests a cyclic cosmos without beginning or end, eternally reborn. However, given what we observe, particularly the presence of dark energy, a Big Crunch seems very unlikely for our universe. The balance of evidence indicates that we are headed toward eternal expansion, either the Big Freeze or Big Rip, with Big Freeze considered far more plausible under current data. Nevertheless, thinking about these scenarios reminds us that our universe's story might have multiple chapters, and perhaps even an epilogue beyond our own cosmos. As we ponder the fate and origin of our universe, we naturally wonder, is our universe the only one, Or is it just one bubble in a vast, frothing sea of universes? Modern theories in cosmology and physics have opened the door to the idea of a multiverse, the possibility that our universe is not alone, but part of a far larger system of universes. The existence of dark energy and the precise balance of physical constants in our universe have led some to wonder if our cosmos is just one of many, its properties one random draw among myriad universes. In a multiverse, what we call fine-tuned constants of nature, like the strength of gravity or the charge of the electron, might vary from one universe to another. We find ourselves in one that permits galaxies and life simply because those that don't would be sterile and uninhabited, with no observers to notice them. One compelling multiverse idea arises from the theory of eternal inflation, a variant of the inflationary scenario we discussed earlier. In eternal inflation, the rapid expansion of space didn't end everywhere at once. While inflation stopped in our region, allowing particles and galaxies to form, other regions of space might still be inflating, or might have ended their inflation at different times, each giving rise to its own bubble universe. Our universe, then, would be one such bubble among countless others, expanding within a larger inflating space-time. Each bubble could have its own distinct laws or constants. Some might be barren, with no matter or with physics hostile to complexity. Others might be roughly similar to ours. Perhaps others are wildly different with more dimensions or different fundamental forces. We cannot directly see these other bubble universes because they would lie beyond our cosmic horizon and indeed beyond any space-time connection with us. But they are a natural extrapolation of inflation theory. These other universes could be as real as our own, each constituting its own reality bubble. The multiverse concept comes in different flavors. The Level 1 multiverse essentially says that if space is infinite and uniformly filled with matter, then far beyond our observable horizon, there could be regions identical to ours, or slightly different or vastly different, simply by random chance arrangements of matter. In an infinite universe, every possible configuration of particles, every possible history, would occur somewhere. Our observable universe would be just one patch of an infinitely vast quilt. The Level 2 multiverse corresponds to the eternal inflation scenario, bubble universes. Each bubble might have different physical constants or particle types, because the process of symmetry breaking in physics could end up differently in each one. One bubble might have a stronger electromagnetic force. Another might have a neutron a bit heavier, preventing stars from working. We find ourselves in a bubble that is congenial to complexity because only such bubbles can produce observers. Another intriguing idea is the Level 3 multiverse, which arises from quantum mechanics, the many worlds interpretation. In quantum theory, every event that has multiple possible outcomes, like a particle decaying or not decaying, is sometimes thought of as splitting reality into multiple branches. According to this interpretation, all possible outcomes actually occur, each in its own branch of the wave function of the universe. So in one quantum branch, universe, the cat is alive. In another, it is dead, to invoke the famous Schrödinger's cat thought experiment. These parallel universes are usually thought to be non-communicating, existing in a superposed mathematical state, rather than separate inflating bubbles. But some argue they are just as real as our own. In effect, this would mean that with every quantum event, the universe, at least at the level of quantum information, splits into multiple histories, creating an ever-branching tree of parallel realities. If true, the number of universes would be mind-bogglingly large and constantly increasing. There is even a conjectured Level 4 multiverse, the ultimate ensemble, which posits that all universes that can be described by consistent mathematical structures exist in some sense. In this view, mathematics and reality are one and the same. Any self-consistent set of physical laws, any mathematical model, corresponds to an actual universe somewhere. This is a philosophical speculation more than a scientific theory, but it underscores how far the multiverse idea can be taken. So, could it be that what we call everything, our observable cosmos, is but a drop in a much grander ocean of existence? It's possible. At present, the multiverse remains a theoretical idea. We have no direct evidence of other universes, and some argue we never could, by definition. Yet the concept finds footing in serious science because it can arise naturally from models like inflation, and because it offers answers to questions like why our universe has the properties it does. They might be random picks from a larger distribution. If the multiverse is real, then the totality of existence is even grander than the universe we've been discussing. It means there could be countless other Big Bangs, countless other expansions, perhaps countless other versions of you and me, or perhaps realities utterly without analogy to anything we know. It is a speculative, almost metaphysical extension of our theories, one that reminds us that as vast as the universe is, there could be more, much more, beyond it. No matter how many universes exist, we know that we can only directly explore our own, and it has plenty of mystery to keep us occupied. One such mystery is deeply connected to our everyday experience, the nature of time. Time flows ever forward, carrying us from moment to moment. We remember the past and anticipate the future, but we never experience events in reverse. This one-way direction of time, from past to future, is called the arrow of time. Why does time have an arrow? The answer, as far as physics can tell, lies in entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics states that in an isolated system, entropy tends to increase or, at best, stay the same. It never decreases spontaneously. This law gives a direction to processes. Things go from ordered to disordered, not the other way around. An egg breaks and scrambles, but a scrambled egg does not unbreak itself into a whole egg. A drop of ink disperses in water, but the ink won't gather back into a concentrated drop on its own. These processes are not forbidden by any fundamental microscopic law. Newton's and Schrödinger's equations work the same forward and backward in time, but they are overwhelmingly unlikely to happen in reverse, because that would require a decrease in entropy. The arrow of time in our universe is fundamentally linked to the initial conditions of the cosmos. The universe began in an extraordinarily low entropy state. This might sound strange because the early universe was a hot, dense plasma which seems very disordered, but in fact, it was extremely uniform and simple, free of complex structures, making its entropy lower than it could have been. It's as if all the matter and energy were evenly spread out and gravitationally unclustered, a very ordered configuration compared to what could be. Because the universe started with such low entropy, there was essentially nowhere to go but toward higher entropy. As the universe expanded and cooled, entropy increased, gradients smoothed out, structures formed even as overall disorder grew. For example, the formation of stars and galaxies increases local order, but overall entropy still rises due to the production of lots of waste heat and the gravitational settling that releases energy. The arrow of time is a manifestation of this rise of entropy. We perceive time flowing forward because that is the direction of increasing entropy. If you were to film a glass shattering and play it backwards, you'd see entropy decreasing and immediately intuit that time is reversed in the film. In the real universe, we do not see such things. One might ask, why was the entropy of the early universe so low to begin with? This remains one of the deep, unanswered questions in cosmology. Some suggest it might be a boundary condition of our universe, perhaps set by a prior state or by the laws of quantum gravity. Others propose that if there are multiple universes or cycles, we naturally find ourselves in one that started in a low entropy state, because only such a universe can develop the complexity needed for observers. Regardless, that low entropy beginning is what allowed an arrow of time to emerge. From it flowed the entire history of structure and complexity. Stars shine, increasing entropy by radiating heat. Life grows and metabolizes, increasing entropy in surroundings even as it creates local order. And eventually stars die and things run down. If we project trillions upon trillions of years forward, in the heat-death scenario, entropy will near a maximum. The arrow of time will effectively fade, not because time has reversed, but because almost nothing changes anymore. There are no organized processes left to distinguish a forward direction. In the far, far future of a big freeze, the universe might reach a state of near equilibrium where, without gradients or differences, the concept of before and after loses much of its meaning. Time and entropy tie together the grand cosmic and the intimate personal. The increase of entropy sets the thermodynamic arrow that makes memory possible. We remember lower entropy past states. It is why we grow older and not younger. It's the reason we can't unmix cream from coffee or unburn a piece of paper. It's fascinating that this everyday irreversibility is rooted in the initial conditions of the entire universe. We've journeyed from the enormous clusters of galaxies to the minute atoms and particles, but we haven't yet delved into the truly fundamental fabric underlying reality, the quantum realm. On the smallest scales, the world behaves in ways that defy our classical intuitions. In the quantum realm, particles are also waves, and everything is described by a fuzzy haze of probabilities rather than definite certainties. Take an electron. In an atom or in transit, it doesn't have a single precise location. Rather, it exists as a cloud of probability, a smeared-out wave of potential positions. Only when we interact with it, measure it, does the electron seem to choose a location or state. This is the bizarre phenomenon of wave function collapse, in interpretations where collapse is a thing. Before observation, Schrödinger's cat is both alive and dead in a quantum sense. Before measurement, the electron has many possible positions. For example, if we shoot electrons at a screen through two narrow slits, something astonishing happens. The electrons, one by one, form an interference pattern on the detection screen, alternating bands as if they were waves that passed through both slits and interfered with themselves. This happens even if we fire them one at a time. It's as though each electron goes through both slits as a spread-out wave. However, if we set up a detector to observe which slit the electron actually goes through, trying to catch it in the act and force it to be a particle going through one path, the interference pattern disappears. Now the electrons behave like little bullets, going through one slit or the other, and no interference fringes form, just two piles behind the slits. The mere act of observation changes the outcome at the quantum level. It's as if nature allows the electron to explore many possibilities, wave behavior, until we insist on knowing which one happened, at which point nature chooses and the wave of possibility collapses into a single result. Empty space itself is not truly empty in the quantum sense. Even in a perfect vacuum, quantum fields are continuously fluctuating. Particle-antiparticle pairs momentarily pop into existence and then annihilate so quickly and so spontaneously that we can barely infer their presence. They leave subtle effects on energy levels and forces. These quantum fluctuations are not just theoretical quirks, they had cosmic consequences. During inflation, those tiny fluctuations in density and energy were stretched out to macroscopic scales. Regions that were ever so slightly more dense or less dense than others became the seeds for all large-scale structure. The spots in the cosmic microwave background that are a bit warmer or cooler, denser or less dense, trace back to these quantum wiggles. It is a breathtaking linkage. The reason galaxies exist where they do is partly because of random subatomic jitter in the universe's earliest moments. The entire cosmic web is essentially amplified quantum noise. Quantum physics underpins nearly everything in our daily experience, even though we don't notice its strangeness on large scales. The atoms in our bodies are held together by electron wave functions and quantum bonds. The sun shines because quantum tunneling allows protons to overcome their electrostatic repulsion and fuse into helium. Without quantum tunneling, the sun's core wouldn't ignite as easily. Computers and modern technology rely on quantum mechanics, semiconductors, lasers. In a sense, the solidity of a rock, the behavior of a chemical reaction, the colors of the rainbow, all trace back to quantum rules. We live in a quantum universe, though its oddness becomes apparent only when we look at small scales or specific conditions. There is also the deep mystery of quantum measurement and reality. Does the wave function collapse when observed? Does the universe split into branches for each outcome? The many worlds idea. No one knows for sure which interpretation of quantum mechanics is correct, or if there's a deeper theory that will resolve these questions. What we do know is that quantum mechanics is astoundingly successful in predicting outcomes. It has been tested to high precision. Reality, at its foundation, is governed by probability waves and uncertainty. It's almost as if nature, at a fundamental level, decides events by a kind of controlled randomness within strict statistical rules. Our voyage has taken us from the beginning of time to the structure of space, from the largest assemblies of galaxies to the subatomic flickers of the vacuum. Along the way, we encountered phenomena that are poetic in their grandeur and scientific in their detail. An afterglow from creation itself still shining to us, invisible matter holding galaxies in its gravitational embrace, a mysterious energy pulling the cosmos apart, and quantum whispers setting the stage for galaxies. Let's return for a moment to that ancient light we freed at recombination, the cosmic microwave background, CMB. After traveling for 13.8 billion years, it reaches Earth as a faint, cold glow in all directions, a few photons per cubic centimeter. In 1965, two engineers, Arno Penzias and Robert Wilson, were using a big horn antenna in New Jersey, trying to eliminate all sources of noise from their radio measurements. They kept encountering a persistent hiss, uniform across the sky, day and night. At first, they thought it might be due to urban interference, or pigeon droppings in their antenna, or instrument malfunction. But none of those explained it. Meanwhile, a group of physicists at Princeton, Dicker, Peebles, et al., had been looking for exactly such a signal. The predicted relic radiation from the hot early universe, which years earlier, scientists like George Gamow had calculated should by now be just a few degrees above absolute zero. Penzias and Wilson had stumbled upon the very signal that those theorists were seeking. It was soon confirmed that this microwave hiss came from all directions uniformly and had a blackbody spectrum of about 2.7 Kelvin, just what the Big Bang model predicted. The cosmic microwave background was the long-predicted afterglow from the hot young universe, now cooled to a whisper. When we map the CMB across the sky, as satellites like COBE in 1989, WMAP in the 2000s, and Planck in 2013 have done with increasing precision, we find it is almost the same in every direction, extremely uniform to about 1 part in 100,000. It's as if the entire sky were painted with one color of incredible smoothness, with only the faintest speckles. Those speckles, the tiny temperature anisotropies, carry a wealth of information. They are the imprints of the primordial sound waves and density ripples in the early universe. The pattern of spots tells us the universe's age, composition, and geometry. By carefully analyzing the CMB, scientists have confirmed the age of the universe, how 13.8 billion years, determined that space is flat to within a tiny margin of error, and measured the ratios of normal matter, dark matter, and dark energy that we mentioned. The CMB is like a baby picture of the universe, taken when it was only 380,000 years old. In that baby picture, we can already see the slight non-uniformities that eventually grew into clusters of galaxies. It's astonishing that we can observe this. When you tune an old television between channels and see static, a small fraction of that static is actually CMB photons. literally relics from the Big Bang hitting your TV's antenna. The CMB also provides evidence that ties together many threads of our story. It confirms the Big Bang. A static universe would not have such a background. It supports inflation. The uniformity and specific patterns match inflationary predictions. And it informs the dark matter models. The CMB pattern is sensitive to the amount of invisible mass. It is a Rosetta Stone for cosmology, decoded through careful, rigorous science. And yet, when one simply gazes at the visualizations of the CMB, with its gentle swirls of red and blue, indicating tiny temperature fluctuations, one can't help but feel a sense of wonder. This mottled oval image, often shown in textbooks and documentaries, is the imprint of the primordial cosmos on the sky, the oldest light we will ever see, a light that has traveled for almost the entire history of the universe to reach us. Within this vast cosmic unfolding, on at least one small planet, the expansion and cooling of the universe eventually led to something new: life and consciousness. The atoms forged in stars and scattered by supernovae became the raw material for new star systems. About 4.6 billion years ago, one particular cloud of gas and dust, already enriched by previous generations of stars, collapsed to form our Sun and its family of planets. The third planet from this sun had the right conditions for a remarkable chemistry. In its early oceans and coastal environments, a rich molecular broth swirled. On this young Earth, a complex chemistry brewed in warm ponds, in tidal pools, and around underwater hydrothermal vents. Complex molecules formed in the warm, wet cradles, perhaps sparked by lightning in the atmosphere or by geothermal energy in the crust, perhaps in sunlit shallow pools left to evaporate on volcanic shores, or in the mineral-rich hot springs on the ocean floor. Simple chemistry crossed the threshold to self-replication. At some point, simple self-copying molecules emerged. This was the origin of life, around 4 billion years ago. From those humble beginnings of primitive microbes, life evolved in complexity and diversity, shaped by mutation, competition, and time. Tiny cells coalesced into more complex cells, which eventually formed multicellular colonies. By around 540 million years ago, the Cambrian explosion filled the seas with an astonishing variety of creatures. Life took hold on land. Plants and fungi colonized the continents, followed by insects and amphibians, then reptiles and dinosaurs. Each living organism was, and is, a little chemical machine, drawing energy from the environment to maintain its internal order, a local reversal of entropy paid for by increasing entropy in its surroundings. In this way, life is a kind of cosmic rebellion against the trend toward disorder, though only a temporary and localized one. Through life, the universe explored an entirely new realm of complexity. After dinosaurs were wiped out 66 million years ago by an asteroid and other factors, mammals rose to prominence. Some primates in Africa, a few million years ago, left the trees for the savanna. They grew bipedal and clever. They made tools and learned to cooperate in groups. By about 300,000 years ago, anatomically modern humans had appeared. With the emergence of Homo sapiens, the universe began to be aware of itself in an unprecedented way. We gazed at the stars with curiosity and imagination. Over thousands of years, we developed language, culture, mythologies about the cosmos. We harnessed fire, energy for entropy consumption. We built shelters. We eventually tilled fields and founded cities. We looked up and saw patterns in the sky, crafting constellations and calendars. Human curiosity pushed us to ask not just how to survive, but why we are here, what the stars are, what the sun is, and how it all began. Fast forward to the modern era. In just the past few centuries, we have, through the scientific method, unraveled many cosmic mysteries. We discovered that those points of light in the night sky are other suns, and some of those suns host planets of their own. We've confirmed thousands of exoplanets and infer that the galaxy holds billions more. We found that our sun is just one star among hundreds of billions in the spiral galaxy we call the Milky Way, and that our galaxy is just one of trillions in the observable universe. We've begun to understand the forces and particles that govern nature. We've peered back in time with powerful telescopes to see galaxies in their infancy, and we've peered into the atom to unlock the secrets of quantum physics. Life, at least here, evolved to consciousness that can contemplate the universe. That is a profoundly poetic fact. We are made of dead stars, and those very ashes have somehow become alive and able to wonder about their origins. The universe spent billions of years evolving us, and through our eyes, it now sees itself. We are a way for the cosmos to know itself, Carl Sagan famously said, encapsulating this truth. Our self-awareness makes the universe not only a physical phenomenon, but also an experience. Through our literature, art, and science, the cosmos has gained the ability to reflect upon itself, to study its own laws, to admire its own beauty. Are we alone in this astounding capability? Perhaps not. The universe is so vast that it seems improbable that Earth would be the only cradle of life. Perhaps in some warm pond on an exoplanet under a distant sun, chemistry has given rise to biology. Perhaps on a moon orbiting a gas giant, beneath an icy crust, alien microbes flourish near thermal vents. Maybe on some planet in the habitable zone of another galaxy, intelligent creatures build their own tools and look up at their sky with questions. As of now, we don't have evidence of life beyond Earth, but the possibility stirs our imagination. Whether life is common or exceedingly rare, the fact remains that life here has transformed a part of the cosmos into something self-aware. And so here we find ourselves, clever, self-aware creatures built of cosmic dust, living on a minor planet, orbiting an ordinary star in a typical galaxy, yet able to contemplate the entirety of existence. Our physical insignificance is undeniable. We are infinitesimal compared to the breadth of the cosmos. Our entire world is just a tiny mote of dust in a cosmic ocean, a pale blue dot adrift among countless stars. But our ability to understand and appreciate the cosmos gives us a significance of a different kind. We might be rare, perhaps the only intelligent beings for parsecs around, or maybe one of only a few in our galaxy. Maybe life teems in the universe, or maybe it is exceedingly scarce. Either way, in our corner of space and time, we are the only known eyes and minds observing the grand cosmic drama. Through us, the universe has become aware of itself. Through our scientific instruments, the universe maps its own structure. Through our poetry and art, the universe speaks of its own majesty. There is something profoundly meaningful about this, even if one views it in a purely secular, scientific way. The cosmos has given rise to beings who can know the cosmos. We have inherited the fiery hearts of ancient stars in the iron of our blood, the calcium of exploded supernovae in our bones, and the carbon and oxygen from countless stellar furnaces in every organic molecule of our bodies. We are literally children of the stars, made of stardust. And those children can now, like grown progeny, look back and study their parents, the stars, and grandparents, the galaxies, the Big Bang. This unity of origins gives us a connection to everything. We are not separate from the universe. We are portions of it, inextricably linked. The laws of physics that formed a galaxy also form the neurons in our brain that fire when we gaze at a galaxy. With knowledge, however, comes the humbling realization of how much we don't know. Our journey through cosmology answers many questions, but raises others. Why is there something rather than nothing? Did time begin with the Big Bang, or is there a multiverse with different realms beyond ours? What is the true nature of space and time on the smallest scales? Are they quantized into discrete bits, as some theories like quantum gravity suggest? We don't yet have a fully unified theory of quantum mechanics and gravity. Thus, the exact first moments of the Big Bang, the Planck time, and what happened before inflation remain mysterious. We still do not know what dark matter is, despite it making up most of the matter in the universe. We still do not know why an early hyperinflation happened, or if it's even the final answer to the early universe's smoothness and flatness. We aren't sure if dark energy is truly constant or has subtle variations, and the nature of dark energy, why vacuum has the energy it does, is deeply perplexing. In fact, theoretical physics calculations of vacuum energy overshoot observations by an outrageous factor, a major puzzle. We do not know if life is a common cosmic phenomenon or an extremely lucky fluke confined to Earth. We have not yet detected signals from other civilizations, though projects like SETI are listening. We do not know the fate of humanity, whether we will spread to the stars or remain bound to our lovely, pale blue dot. In short, we still float on a sea of mystery, with islands of knowledge gained so far. Standing at this precipice of knowledge and mystery, one cannot help but feel a profound awe. The universe is ancient and vast beyond comprehension, yet here we are, small creatures with curious minds, capable of tracing its story from the primal fireball to the present, and even forecasting its possible futures. That story, from the simplicity of the early fireball to the complexity of a living world, is both humbling and inspiring. The cosmos is breathtaking, not just in scale, but in the way it has produced patterns and coherences. The periodic table of elements forged in stars, the spiral patterns of galaxies, the double helix patterns of DNA that allowed creatures like us to emerge. There is a deep harmony in how the same physical laws apply across all scales. The nuclear reactions blazing in the core of a distant star obey the same physics as the glow of your reading lamp. The gravity that makes a planet orbit the sun is the same gravity that makes galaxies dance around one another in clusters. Mathematics, abstract patterns of logic, proves to be an incredibly effective language to describe these laws, suggesting a wondrous connection between the human mind and the workings of the universe. It's as if the universe has a hidden symmetry or order that we can glimpse through mathematics and science. Our journey of understanding is far from over. Each new discovery in astronomy or physics tends to open new questions. When we discovered the expansion of the universe, we were led to ask about the beginning, Big Bang, and the ultimate fate. When we found the cosmic microwave background, we were led to the idea of inflation. When we observed unexpected galaxy rotations, we hypothesized dark matter. When we measured distant supernovae, we stumbled upon dark energy. Every time we peel back a layer of reality, there is another layer waiting, sometimes with stranger questions. This is the beauty of science and exploration, a continuous unfolding story, each chapter building on the last, but the book seemingly without end. Picture the cosmic timeline as a grand narrative, a story that begins with nearly featureless energy and evolves into intricate worlds and beings. It's a story that spans 13.8 billion years and perhaps will span trillions more. To grasp our place in this timeline, imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. By early February, the first stars ignite. By mid-March, galaxies are forming. The Milky Way might form around May. Our Sun and Earth appear roughly in early September on this cosmic calendar. Life arises on Earth by late September. Complex multicellular life proliferates in November. Dinosaurs roam the Earth on December 25th, Christmas Day, and go extinct on December 30th. Modern humans emerge only in the final hour of New Year's Eve, and all of recorded human history flashes by in the last seconds before midnight. In those final seconds, we develop agriculture, build the pyramids, invent the telescope, land on the moon, and contemplate the Big Bang. When the clock strikes midnight to herald a new cosmic year, Perhaps that represents some distant future state we've yet to comprehend. This cosmic calendar shows just how young we are. Human civilization is an eye blink in cosmic time, and even the Earth is a relatively late chapter in the story. We arrived at the tail end of the year, so to speak, but armed with curiosity and intellect, we busied ourselves in those last seconds learning about all that came in the months before us. Now we, ephemeral yet mindful, look to the future. We wonder what's next for the universe and what's next for us. Barring extraordinary intervention, the universe will continue to expand and evolve according to the physical processes we have discussed. As for humanity, we too are subject to cosmic forces, but have some say in our destiny if we are wise. We may spread to other planets, carrying our legacy of curiosity with us beyond Earth, ensuring that life and consciousness have a longer future than our single planet's fate. We may find ways to harness new energy sources or manipulate space-time, ideas once in the realm of science fiction, but who knows what knowledge awaits in the coming millennia. Or we may struggle and someday perish, becoming a brief spark that faded out. But even if our particular lineage ends, perhaps other intelligences elsewhere will carry on, or new intelligences might evolve from what we leave behind, intelligent machines, or new species. The desire to know and to wonder might itself be as resilient as life. From the standpoint of the universe, meaning is not something handed down from the stars. It is something we create. We infuse the cosmos with meaning by contemplating it. A galaxy 100 million light-years away has no idea of its grandeur. But we know, and in knowing and seeing beauty in it, we give it meaning, at least to us. In a way, the cold equations of physics blossomed into the warmth of human experience and inquiry. The universe is often described as a cold, uncaring place, and physically it is vast and mostly inhospitable. But through us, it cares about itself, in the sense that we care and we are part of the universe. This connection may be philosophically subtle, but it is emotionally powerful. Our exploration is ongoing. Even now, new telescopes like the James Webb Space Telescope peer into the distant past, seeing galaxies forming just a few 100 million years after the Big Bang, giving us new data points in the cosmic saga. Particle accelerators, like the Large Hadron Collider, probe higher energies, trying to recreate conditions just after the Big Bang, searching for clues of new physics. Perhaps particles that could explain dark matter or hints of extra dimensions. Experiments in deep mines attempt to catch a glimpse of dark matter particles zipping through Earth. Space probes explore planets and moons, looking for signs of past or present life beyond Earth. Mars's ancient riverbeds, the subsurface ocean of Europa, the methane seas of Titan. We are, in a sense, turning over every stone we can in this universe to piece together the puzzle of reality. Standing on the precipice of all this knowledge and mystery, we feel both incredibly small and incredibly enriched. The night sky no longer just offers twinkling points of light. It is a time machine, showing us distant galaxies as they were eons ago and connecting us to the moment of creation. The ground beneath us is not just dirt, it's ancient cosmic debris, a mix of elements made in star cores, arranged by geological and evolutionary processes into our immediate environment. We, the curious specks of the universe, will keep lighting candles in the cosmic dark, striving to illuminate more of that everything, even as it continually surprises us. The quest goes on, and the wonder deepens. To be alive as a human at this moment, to have consciousness, to have the accumulated knowledge of generations at our fingertips, and the ability to extend that knowledge, is a precious, fleeting gift. Through our minds, the universe has awakened to a sense of itself, however partial. We have the privilege of witnessing this vast tapestry and the responsibility of carrying that knowledge forward. In the end, the story of the universe is not just a tale of matter and energy moving heedlessly. It is also a human story, a story of awareness and curiosity finding a foothold in a vast cosmos. We began this journey meditating on the concept of everything. Now, At journey's end, we realize that perhaps we have only scratched the surface of everything. We close with more questions than we started, but also with a deeper reverence for existence. We sense that the strangeness and wonder of the universe will never end, no matter how much we discover. As long as there are beings curious enough to look up and ask questions, the cosmos will continue to inspire. In its darkness and its light, its simplicity and its complexity, its silence and its stories, the universe offers an endless well of awe. It is a beauty we could pursue forever and never exhaust, or without end. We float in the darkness between stars, a small collective of minds gazing up in wonder. We stand under the night sky, awash in starlight that left its sources millions of years ago. Above us arcs the Milky Way, a pale river of stars flowing across the heavens. In its gentle glow, we feel both tiny and profoundly connected. We know that each pinpoint of light is a sun like our own, burning with the same kind of fire. The iron in our blood was forged in such stars long ago. The gentle silver glow of the galaxy reminds us we are made of this universe. We have always been children of the stars, built from their dust, shaped by the physical laws that govern everything we see. The cosmos is vast and old, yet it obeys the same simple truths everywhere. The same chemistry that lets us breathe traces across the spectrum of distant suns. The same gravity that pulls an apple to Earth binds the swirling arms of distant galaxies. There is an eerie harmony to it all, as if the universe knows how to stay consistent with itself. We share this cosmic stage with countless stars and at least as many questions. On a clear night, as we peer into the depths, we find order amid the chaos. Galaxies dance in clusters, bound by gravity's invisible web. Stars live and die, spreading heavy elements that will become new stars, planets, maybe life. There are fundamental numbers, the strengths of forces, the masses of particles, the speed of light, that seem precisely tuned to weave this cosmic tapestry. If the forces of nature were only slightly different, perhaps atoms could not hold together, or stars could not shine long enough for life to arise. But here we are, in a universe that lasts billions of years, with stars that furnace the elements of life, and a planet just temperate enough for us to ponder it all. It's a breathtaking balance. In the grand cosmic darkness, the laws of physics serve as a steady beacon, guiding the formation of everything from the smallest atom to the largest galaxy. Our universe appears to be a harmonious whole, governed by elegant rules that we have only begun to decipher. Under this starry dome, it's natural to feel that our universe is complete unto itself. For generations, we've used the word universe to mean all there is, the totality of existence, everything that ever was or will be. We have believed, as Carl Sagan once poetically intoned, that the cosmos is all that is, or ever was, or ever will be. Our ancestors saw the stars as eternal and unchanging lanterns in the firmament. Today we know those lights are distant suns, but we still assume the collection of them, the universe, is the ultimate container of reality. It contains us, our planet, our galaxy, and all the far-flung galaxies we observe. It's immense beyond our imagination. Hundreds of billions of galaxies, each with billions of stars, spread across space that has been expanding for nearly 14 billion years since the Big Bang. Standing in the hush of a midnight landscape, seeing the infinite stars overhead, we are tempted to think this is everything, that beyond the glittering boundary of what we can see, there is only endless darkness. And yet, a question quietly rises, like the soft glow of pre-dawn. What if this isn't all there is? What if the magnificent expanse we call our universe is only one drop in a much grander cosmic ocean? As we let our eyes drift across the sky, we cannot help but wonder. We humans have had to expand our perspective many times before. Once, we thought our Earth was the center of everything, until we learned it is one planet among many orbiting the sun. Then we thought our sun was unique, until we found it is one star among billions in the Milky Way. We believed our galaxy to be the entirety of creation, until other galaxies were discovered, filling the universe in every direction. Each time, we've had to surrender a bit of our cosmic self-importance and accept that the universe is bigger and more varied than we knew. Now, a new revolution in thinking may be upon us, the idea that our entire universe might not be the only universe. Perhaps it is we who are in a bubble, one realm among countless others. The word universe, meaning everything, might itself be too limited. What lies beyond everything we know? This is the startling possibility that scientists and philosophers are grappling with in the idea of the multiverse. A multitude of universes, perhaps infinitely many, existing in ways we are only beginning to theorize. It sounds like science fiction. Other universes with other stars, maybe even other versions of ourselves. Yet this concept did not arise from idle daydreams. It emerged from deep puzzles in physics and cosmology. As we peer closer at the fundamentals of our universe, its origin, its laws, its quantum underpinnings, we find hints that our cosmos might be just one of a far larger collection. Why is our universe so hospitable to life? Why did it start with just the right conditions for galaxies to form? What happens at the edges of space and time, or inside a black hole? Modern science suggests answers that lead to a profound outlook. Our universe may be one node in an endless cosmic web of universes. For a moment, let's linger on that thought. If true, it would mean when we look up at the night sky, we are not just seeing all that is, but merely our own local neighborhood within an unimaginably vast ensemble. It would mean that beyond the cosmic horizon of 46 billion light-years, beyond the furthest galaxies we can ever see, space might keep going and going, potentially forever. And if space goes on forever, then logically, somewhere far beyond any hope of observation, there could be other regions of the cosmos entirely disconnected from ours, perhaps even following different scripts of reality. Could it be that the starry sky we see is like one page in an infinite book, a book with every possible page? The notion is as exhilarating as it is disorienting. Our heartbeats quicken at the bravery of asking such a question. Is our universe just one of many? We take a deep breath, steady our thoughts, and step through the looking glass into this radical idea. To explore the multiverse, we must journey back to the very beginning of our universe, to the first fraction of a second after the Big Bang. In that embryonic moment, according to our best theories, an extraordinary thing happened. The universe expanded at a stupendous rate, far faster than the speed of light, ballooning from subatomic size to astronomical size in the blink of an eye. We call this event cosmic inflation. It's a powerful idea developed in the 1980s to solve several riddles about the early universe. Why is the cosmic microwave background, the afterglow of the Big Bang, almost the same temperature everywhere we look? Why is space so flat and smooth on large scales? Inflation provides answers. A burst of exponential expansion stretched the young universe, smoothing out irregularities and flattening space, much like inflating a crumpled balloon. When we look at the sky today, the uniformity we see in the afterglow is the fingerprint of that inflationary era. The evidence for inflation has grown persuasive. Subtle patterns in the microwave background radiation and the distribution of galaxies align with what inflation predicts. It's not proven beyond all doubt, but most cosmologists have embraced inflation as a key chapter in our cosmic history. Yet inflation, in solving old mysteries, opened a door to an even grander possibility. The very equations that describe inflation imply that it may not have been a one-time event that neatly began and ended everywhere. Instead, inflation could be an ongoing process, still happening in distant regions beyond our view. The idea is called eternal inflation, and it works like this. Quantum fluctuations in the infant universe meant that different parts of space ended inflation at different times. Our entire observable universe is thought to be one pocket, one bubble, where inflation stopped and normal expansion took over, allowing matter to coalesce into galaxies and stars. But elsewhere, beyond our bubble, other regions might still be inflating or have inflated at different rates, budding off their own bubbles of space-time. In this picture, the Big Bang isn't a unique event. It's happening over and over in a vast inflating background. New universes, bubble universes, are constantly being born like foam on the crest of an endless wave. Imagine the multiverse as a great cosmic foam, with bubble universes instead of soap bubbles. Each bubble is a self-contained universe, rushing outward, separated from its siblings by regions of still inflating space that stretch faster than light, preventing the bubbles from easily colliding or interacting, though perhaps occasionally they might, like bubbles bumping in a bath. Our universe would be just one bubble in this frothy sea. Inside our bubble, we see the aftermath of our own Big Bang. We see galaxies flying apart as space expands, but our bubble has an edge beyond which we cannot see or travel. And beyond that edge, more bubbles, more Big Bangs, more universes. Inflation never completely ends. It keeps spawning new universes indefinitely, some perhaps even infinitely far away. This concept transforms the Big Bang from the beginning of everything to the beginning of our local universe, one patch amid an eternally growing mosaic. We find ourselves no longer at the center of the stage, not even the only stage. We are on one island, in an infinite cosmic archipelago. In this scenario, space itself is unimaginably vast, possibly infinite, and carved into domains, bubbles, each a cosmos in its own right. What would those other universes be like? They might be broadly similar to ours or wildly different. Some could be almost empty, inflation ending in them in such a way that few particles condense, barren voids with no galaxies. Others might be dense and violent, collapsing in on themselves or never cooling enough for stars. Crucially, the laws of physics might be different in each bubble. This isn't just speculation. It arises naturally when we combine inflation with another leading theory in physics, string theory. String theory attempts to unify all forces of nature by positing extra dimensions of space and tiny vibrating strings as fundamental ingredients. It's a bold, mathematically rich framework. One striking feature of string theory is that it doesn't predict a single unique outcome for the properties of our universe. Instead, it seems to allow a vast number of possible worlds, each corresponding to a different way the extra dimensions can be curled up or the strings can vibrate. Physicists call this huge range of possibilities the string theory landscape. Estimates suggest there could be on the order of 10 to 500 different self-consistent universes in this landscape. A number so huge, it defies comprehension. That's a 1 followed by 500 zeros. An astronomically large number of possible universes. If string theory's landscape is real, our universe is like a tiny oasis in a desert of possibilities. Why did we get this particular set of physical constants and not another? For decades, scientists hope to find a principle that picks out exactly our universe from the myriad possibilities, some fundamental reason our cosmos had to be the way it is. But so far, no such principle has been found. Instead, an idea gained traction. Maybe all those possible universes exist somewhere in the multiverse, and we find ourselves in this one because, out of the spectrum of possibilities, this is one of the rare universes where conditions allow observers like us to arise. This line of thinking is known as the anthropic principle, specifically applied to the multiverse. It says, consider that we can observe this universe. That simple fact biases what kind of universe we should expect to observe. We couldn't exist in a universe where, say, gravity was so strong that the universe collapsed in a second, or so weak that no stars formed. We couldn't marvel at the stars in a universe with no stars. So perhaps there are countless universes with varied physical constants, and naturally, we find ourselves in one of the Goldilocks universes. Not too hostile, not too sterile, but just right for life. This isn't a teleological or mystical argument. It's a kind of cosmic selection effect. Out of a multiverse of all sorts of universes, we, the observers, will only be in those universes that can support observers. It's a profound and somewhat unsettling idea. It means that many of the miraculous coincidences that make our universe habitable, the precise strength of the strong nuclear force, for example, which if slightly different would prevent stars from synthesizing carbon, or the value of the cosmological constant, the energy of empty space, which is so small that galaxies had time to form, might not be miracles at all, but simply one lucky ticket in a giant cosmic lottery. Our universe won the lottery of existence, allowing complex structures and life, but there were many, many tickets, universes, that were drawn. We naturally wake up in a universe that's a winner, because only winners get to have someone wake up and ask the question. This anthropic reasoning is controversial. Some scientists find it unsatisfying, akin to saying, "We're here because we're here." Others point out that it did make a successful prediction. Decades ago, physicist Steven Weinberg used anthropic arguments to estimate the cosmological constant's value, reasoning that if it were much larger, galaxies wouldn't form and we wouldn't be here. His estimate was on the right order of magnitude to what was later observed as dark energy. That gave some credence to the idea that perhaps our universe's properties are drawn from a random distribution of possibilities across a multiverse. So inflation gives us a picture of an ever-growing, bubble-populated multiverse, and string theory suggests each bubble could have different physics, forming a patchwork of realities. The multiverse as a cosmic quilt, each patch a universe with its own pattern. We might inhabit a patch where the forces and particles are tuned just so, while far off in another patch, the fundamentals might be shifted. Maybe that universe has heavier electrons, or a faster speed of light, or even different numbers of dimensions. It boggles the mind to consider the variety. Many of those universes would be dull or inhospitable. Just as most of space in our own universe is cold and empty, most universes might not host life. But in an infinite ensemble, even rare conditions, like the specific mix that allows life, will occur infinitely often. Infinity has a way of making even the rarest outcomes inevitable somewhere. If space is truly endless and inflation eternal, then somewhere, right now, there are fantastical worlds. A galaxy where every star is encircled by habitable planets, or a universe where purple clouds of cosmic dust think thoughts. And also, scattered in the multiverse, would be countless worlds nearly identical to ours. In an infinite expanse, eventually the patterns of particles that make up you and me will repeat by chance. It's been estimated, in a straightforward infinite space scenario, that the nearest exact duplicate of our observable universe could be incredibly far, 10,118 meters away, a number so huge we can barely fathom it. But if space truly goes on forever, somewhere out there, that duplicate exists. And not just one, infinitely many. This isn't even invoking exotic theory. This is a consequence of simple infinity plus the finite ways particles can arrange. It's a mind-bending implication. The multiverse could contain other people who are, to all intents and purposes, you, living out every alternative history that could have befallen you. Before that notion makes us lose our grip, let's step back and approach the multiverse idea from a different angle. One that doesn't even require distant, unreachable corners of space, but might be unfolding right here and now, in tandem with our own lives. This brings us to the quantum realm, and to the many worlds interpretation of quantum mechanics. At first glance, this has nothing to do with the bubble universes of inflation. It's a separate thread, born from the mysteries of the subatomic world. Quantum physics famously tells us that particles can exist in a superposition of states. They can literally be in two or more conditions at once, like a spinning coin that is both heads and tails until we catch it. Only when we observe or measure the system does it seem to choose an outcome. For example, a single electron can pass through two slits at the same time and interfere with itself, a behavior which defies classical logic. In the traditional view, the Copenhagen interpretation, the act of measurement causes the set of possibilities to collapse to one actuality. Why or how that collapse happens is still debated. It's as if nature randomly selects one path for reality to take, out of many potential ones, at the moment of observation. In 1957, a bold young physicist named Hugh Everett III proposed a different solution. What if the wave of possibilities never actually collapses? What if instead, at each quantum event, the universe splits into branches, each branch realizing one of the possible outcomes? In one branch, the electron went through the left slit. In another, it went through the right. When you measured it, you became split as well. One version of you seeing the electron here, another version seeing it there. Each version is real, but they exist in separate, non-communicating parallel worlds. At the moment of measurement, reality's timeline forked. According to Everett's many worlds interpretation, MWI, this is happening constantly, all around us, at the microscopic level, and by extension, at the macroscopic level too, since every big thing is made of quantum particles. The entire universe is continually branching into countless parallel universes. It sounds like something out of a fantasy novel. Every decision, every chance event spawns a new world. But this idea is grounded in the same rigorous mathematics that makes quantum mechanics the most successful physical theory we have. Everett argued that if the equations say a particle can be in multiple states, maybe it truly is. And the only reason we experience a single outcome is that our consciousness follows a particular branch. Other outcomes play out as well, but we, this particular copy of us, only witness one. Another copy, another we, witnesses the other outcome, and neither version can interact or even know about the other after the split, because the whole universe's state has separated into non-interfering branches. Let's make this more concrete with a whimsical example. Suppose we flip a quantum coin, perhaps by measuring the spin of an electron, which has a 50-50 chance to be spin up or spin down, analogous to heads or tails. According to many worlds, when we check the result, the universe bifurcates. In one universe, we see the coin come up heads. In another universe, we see it as tails. In that moment, two versions of us emerge, each unaware of the other, each continuing forward, believing that our coin toss gave a definitive result. It didn't feel like a split. Each of us experienced a perfectly ordinary coin toss with a single outcome. But collectively, the deeper reality now encompasses both outcomes. Extrapolate this to every quantum event everywhere. Atoms decaying, neurons firing, photons reflecting. The rate of branching is beyond colossal. Effectively, with each fraction of time, the number of parallel universes multiplies, containing every possible way events could have unfolded. By this view, the entirety of creation is a constantly splitting tree, with trillions upon trillions of twigs sprouting each instant, each twig a full universe with a distinct history. It's an almost overpowering picture. If it's true, then right now there are unimaginably many versions of you living out other lives. Most of those versions are nearly identical to you, differing maybe only in what you had for breakfast yesterday or whether you sneezed an hour ago. Some are more divergent, versions of you who pursue different careers, live in different cities, speak different languages. For every choice you've ever wondered about, what if I had taken that other job? What if I had said yes instead of no? There is, if many worlds is correct, a universe out there where you did exactly that. Even for outcomes beyond your control. What if the storm hadn't hit? What if my favorite team won the championship? The alternatives happened in other branches. It's a multiverse not separated by distance, but by decoherence in quantum phase space. A fancy way of saying, the worlds occupy the same space, but cannot interact after they split, like ghostly layers of reality that are intangible to one another. They're here, but out of reach, each as real as the one we know. The many worlds multiverse is different in character from the cosmic bubble multiverse. but they're not mutually exclusive. In fact, if both theories are true, every bubble universe born from inflation might in turn branch into quantum many-worlds, creating a kind of nested multiverse, an ever-branching fern of universes sprouting off other universes. But even on its own, the quantum branching idea profoundly changes how we see our place in reality. We might say, in a way, that the universe is remembering every fleeting possibility by giving it its own world. Nothing is forgotten or discarded. No potential outcome is truly lost. If something could happen, it does, each in its own branch. This notion of parallel worlds has seeped into popular imagination through science fiction, but here we're discussing it as a serious interpretation of physics. Many worlds has gained more acceptance among physicists in recent decades, especially as it offers a straightforward, if extravagant way, to make sense of quantum puzzles without requiring a special, ad hoc rule for observers. In many worlds, there is no mysterious wave function collapse. The wave function, the mathematical description of a system's possibilities, just keeps evolving smoothly. The collapse we perceive is simply us finding ourselves on one branch. In the grand scheme, the wave function of the cosmos contains all branches at once. From a bird's eye view, there is just one quantum universe, one multiverse, evolving deterministically, encompassing every possibility. From our limited frog's eye view inside one branch, we see randomness and choice, not realizing the other outcomes also came true, just not in our world. As mind-boggling as the multiverse of many worlds is, we must acknowledge it might be unprovable in the usual sense. The alternate branches cannot be contacted. They drift out of phase permanently. Similarly, the bubble universes from eternal inflation are separated by more space than light can ever traverse, so we cannot see or travel to them. Critics of multiverse ideas often point out that if these other universes are forever unobservable, can we truly call this science? It's a fair question. Proponents argue that if a theory that we can test, like inflation, predicts a multiverse as a natural consequence, we shouldn't ignore that prediction just because it is difficult to verify directly. We might find indirect evidence or at least consistency checks. For example, while we cannot see other bubble universes directly, they might have, in rare cases, collided with our bubble in the distant past. Such a collision could leave a subtle round pattern in the cosmic microwave background, a bruise on the sky. Physicists have actually searched our sky maps for hints of such bubble collisions. So far, none has been convincingly found. If one day a circular anomaly in the microwave background were detected, consistent with another universe grazing ours long ago, it would be a groundbreaking, if indirect, confirmation that we're part of a multiverse. Similarly, with many worlds, while we can't hop between branches, experiments in quantum physics, like interference experiments with ever larger objects, continue to validate that superpositions are real. Many worlds takes those results to their ultimate conclusion. As our theories develop, we might even find more than one reason to believe in a multiverse. It's intriguing that completely independent lines of inquiry, cosmology on the largest scales, and quantum physics on the smallest, both hint at universes beyond our universe. And string theory, operating at the nexus of quantum gravity, adds its own multiversal flavor with the landscape of possibilities. These ideas paint different portraits of the multiverse, but they could be facets of one grand truth. Perhaps our reality has layers, the vast physical multiverse of regions beyond our view, sometimes categorized by physicists as Level 1 and Level 2 multiverses, with Level 1 being just an extension of our space, and Level 2 being different bubbles with different constants. The quantum multiverse of branching outcomes, Level 3 in one classification scheme, and even the ultimate abstract multiverse of all possible mathematical structures, Level 4 in that scheme. That last one, the Level 4 multiverse, is a conjecture by cosmologist Max Tegmark that every self-consistent set of laws, every mathematical structure that could describe a universe, is realized as its own universe. In such an ultimate multiverse, not only are constants different, but the very laws and fundamentals could differ. Universes with different numbers of dimensions, or entirely different particles, or physics beyond our imagining. It's a speculative idea, bordering on philosophy. In the realm of all possibility, nothing is forbidden. If such a level 4 multiverse exists, our bubble of a universe is just one equation in the library of all equations. We mention this cosmic vision to acknowledge how far the multiverse concept can go. It's the broadest possible extension. Everything that can exist does exist in some universe. In a sense, it would answer the question, why is there something rather than nothing, by suggesting that nothing is just one option, but in the grandest multiverse, every option is instantiated. Thus, there is something, and indeed, everything. But even leaving aside that extreme level, the more grounded multiverse ideas give us plenty to ponder. Let's now gently descend from these theoretical heights and consider what it means for us if we truly live in a multiverse. How do we find meaning and identity in an existence where there may be countless duplicates of ourselves and innumerable worlds, with perhaps no obvious connection to ours? It can feel overwhelming, even disorienting, to contemplate that in the cosmic grand scheme, our entire observable universe, everything we've ever seen, might be a speck, and a redundant speck at that, one of infinitely many similar specks. It raises profound questions about significance, purpose, and uniqueness. One immediate question is about identity. We normally think each of us is a singular individual with a singular history. If the multiverse is real, especially the quantum many worlds multiverse or the infinite space multiverse, then there are other yous out there. Some are extremely close to you, differing perhaps only by a single thought or atom's position. Others diverged more significantly at some juncture. Are those people you in any meaningful sense, or are they merely separate individuals who happen to share your name and genetic makeup and memories up to a point? This isn't entirely abstract. Consider an analogy. Identical twins share nearly the same DNA and often a similar upbringing, but we still regard them as two persons. Parallel selves in alternate universes might be thought of similarly. Each one is a unique person, even if at one time they were the same person. Before splitting or before diverging, conditions made them different. We might need to rethink what we mean by self. Perhaps we're not an indivisible essence, but rather a collection of potential selves, only one of which we experience directly. In one philosophical view inspired by the multiverse, who you are could be seen as a story, a narrative thread through one sequence of events. Your other selves have different narratives. Each narrative is valid and complete in its own universe. We, in this universe, are following one particular storyline. Our other selves follow their storylines. We branch like the limbs of a tree, sharing roots and trunk, our past, then splitting into separate boughs. Is the tree as a whole us, or is each branch a different us? It might be a matter of perspective. There's a poetic notion in the multiverse context. We are like a branching tree or a splitting amoeba, continually dividing. The I that exists after a branch may not be aware of the other branches, but collectively, they all originated from the single organism that was I before. This can trigger a mini identity crisis if we take it seriously. Am I just one of many? And if so, does my life matter less or more? One could argue it becomes more precious. I am the only version of me that gets to experience this particular sequence of events. Yes, there are uncountable other versions, but their experiences are theirs, and mine are mine. I, this branch of me, will never get to see what happens in the other branches, so for all practical purposes, my reality is the one I have. In that sense, nothing changes. I still must make choices and find meaning here. Alternatively, one could derive a sense of comfort that somewhere, Another me makes choices I regret not making, or achieves goals I failed to achieve, or keeps alive those I lost. But equally, somewhere I may experience tragedies I've been fortunate to avoid. It's a double-edged sword. What about morality and responsibility in a multiverse? If every possible outcome happens, does that diminish our responsibility for our actions? One might think, in another universe, I did otherwise, so what does it matter what I do here? But from the standpoint of each universe, consequences are very real. If I choose to be kind in this world, someone in this world is helped. That doesn't get erased by the fact that in another world, I might have been unkind. Each branch is separate and actual. We can't excuse misdeeds by pointing to another branch where we did good. Our local moral reality is what counts for us and those around us here. However, the multiverse could make us more empathetic to the range of human or cosmic experience. For anything someone can go through, there is likely a universe in which it occurs. It's a strange kind of consolation and caution at the same time. It might also challenge religious or spiritual views. For instance, if one believes in a guiding plan or singular purpose, a multiverse complicates that. Is there a separate plan for each universe, or one plan that encompasses all? If a deity exists, perhaps the multiverse concept elevates that deity's creativity to infinite heights, creating not just one universe but a boundless array. Or conversely, some might feel the multiverse removes the need for a creator entirely, as it could explain fine-tuning without invoking design. These are deep waters where science and philosophy meet, and each of us may come to different personal conclusions about them. Let's step away from the heavy epistemology and imagine in a more playful way what the multiverse implies. It means every dream is somewhere a reality. Perhaps not literally the kind of dream you have at night, but any coherent scenario you can think of likely exists in some universe. A world where dinosaurs never went extinct and evolved intelligence. Physics doesn't forbid it, so it's probably out there in an alternate history. A planet where the continents formed a different shape, where an empire that fell in our history prospered in another timeline. The multiverse can be seen as a grand cosmic library of all possible stories. We happen to be leafing through one particularly engaging book, our life, our universe. But around us, on shelves stretching to infinity, are all other books that ever could be written. Some nearly identical to ours, some radically different genres altogether. This literary metaphor might bring a certain comfort. Our joys and sorrows, unique as they are to us, are also part of a vast tapestry of all joys and all sorrows that can ever be. We are not alone in any absolute sense. Existence in its totality contains others who have felt what we feel, done what we do, in one universe or another. In one sense, the multiverse can make us feel extraordinarily small, one tiny being, in one tiny universe, among who knows how many. But in another sense, it can make us feel profoundly connected, part of a much larger existence, threads in a boundless cosmic cloth. There is also the perspective of humility and open-mindedness that the multiverse invites. If our universe, the grandest thing we know, is just a drop in a sea, then the lesson of Copernicus continues. We are not the center, and even the reality we take for granted is not the whole show. That doesn't diminish the beauty of our world. In fact, it may enhance it. How special that, in an infinite multiverse, we have this particular universe to call home. Out of a multitude of possibilities, we get to experience this one, with its specific sky, its particular laws, its unique living earth. It's like being dealt a particular hand of cards from an infinitely large deck. The odds of getting exactly this hand were infinitesimal, yet here it is, and it's the only hand we'll play in this game. That realization can instill a renewed awe for the gift of existence. We look at the sun and think, in other universes there may be different suns or no sun at all, but here we have this golden star warming our days. How marvelous. We taste a peach or listen to a melody and realize this experience might be rare in the grand ensemble of universes. What a privilege to be among the beings who can taste and listen. As we near the end of our journey through the multiverse, we find ourselves returning to where we began, under the canopy of stars, but with our minds expanded and our hearts contemplative. What have we learned? We learned that current science, as far as it has pushed, allows reality to be far larger and more varied than what we directly see. We learned that our universe might be just one wave on an endless ocean, one bubble in a boiling cosmic pot, one branch on an ever-dividing tree of realities. We entertained the possibility that our dearest laws and constants might be parochial facts, different in another universe, that our life here is one of many lives we might be living across parallel worlds. We considered how that might reframe our sense of self and our search for meaning. Yet after all that, we have also learned that the here and now still matters, perhaps more than ever. The multiverse idea, rather than making everything meaningless, can make everything meaningful in its own local context. Each universe is like a poem, complete in itself. The existence of other poems doesn't reduce the beauty of this one. Our narrative, the story of us in our universe, is still unique to us. We remain the authors of our choices and the caretakers of our world. If indeed the cosmos is remembering every possibility through the multiverse, then living our lives authentically is our way of contributing to that cosmic memory. We are the universe, or multiverse, experiencing itself in one of myriad forms. There's something profoundly poetic about that. It suggests a unity behind the diversity. Just as millions of cells make up one organism, perhaps countless universes all exist within one overarching reality. We might never observe those other universes, but through science and imagination, we can feel a sense of their presence. In a way, contemplating the multiverse brings us a sense of companionship in the cosmos. The vast loneliness one might feel, thinking of how empty most of space is, could be alleviated by imagining that beyond our horizon are other universes brimming with their own wonders. Some might harbor life, minds, civilizations, utterly alien or perhaps oddly familiar. We cannot know, but it's intriguing to think that creation did not stop with our world or our universe. Nature, it seems, never runs out of creativity. The multiverse would be the ultimate expression of fecundity, an infinite garden of worlds where all possibilities bloom. Now, as we let these ideas settle, we might worry, will we ever be sure the multiverse is real, or will it remain forever a tantalizing hypothesis? It's possible we may find stronger evidence, a clear sign of a universe beyond ours imprinted in subtle data, or a theoretical breakthrough that virtually demands the existence of other universes. Or we may find that our theories were mistaken or incomplete, and the grand multiverse doesn't exist as we conceived. That is the nature of science. It evolves. But whether or not the multiverse is physically true, exploring it in our minds has value. It stretches our imagination and challenges our assumptions about reality. It teaches us not to take everything for granted as truly everything. There may always be more beyond, unknown domains to discover or conceive. In the end, thinking about the multiverse is a bit like standing at the shore of an endless sea at night. We see the dark waves and hear their roar, but we cannot see across to the other side. In fact, there may be no other side. We know not what lies over the horizon of water and darkness. It could be more ocean, stretching out without limit. We suspect it is. And perhaps, out there in the cosmic ocean, there are other explorers on other shores, under other skies, wondering if anyone else is out there. In our universe, on our small planet, we've long wondered if we are alone in the cosmos. The multiverse concept extends that wonder to our universe itself. Is our universe alone or one of many? It is a profound shift of perspective, yet somehow a natural continuation of the trajectory we've been on since Copernicus. Every time we thought we were singular, we found we were part of a multitude. Why should universes be any different? Nature has shown a love for prolific abundance, countless stars, countless galaxies. Perhaps it also made countless universes. As we conclude this exploration, let's allow ourselves a moment of quiet reflection and awe. Above us, the night is still and clear. The stars shine down indifferently, as they have long before we understood any of this. We realize that even if there are infinite universes, we still only see our sky, and it is beautiful. The multiverse, if it exists, doesn't make our universe any less wondrous. In fact, it makes every glint of starlight even more poignant, knowing that it might be one of uncountable stories. And yet it is our starry sky, our chapter of the cosmic tale. We feel a sense of gratitude for being alive in this vast, enigmatic reality, whatever its true extent may be. We turn our gaze from the heavens to each other. We, the collective voice in this narrative, represent all of us together, trying to understand existence. In confronting the idea of the multiverse, we have shared a journey of imagination grounded in science, and science elevated by imagination. It's a journey that has taken us to the borders of knowledge and beyond, into realms that test the limits of language and thought. Such a journey can be humbling. It reminds us that there is so much we don't know, but it can also be inspiring. It shows that we as humans have the capacity to envision realities far beyond our mundane experience. Perhaps someday in the distant future, our descendants will find ways to gather more evidence or even harness knowledge of the multiverse. Or maybe the multiverse will remain an eternally tantalizing concept, never fully confirmed. Either way, it changes us in the here and now. It expands our conception of what reality could be. It invites us to partake in a cosmic perspective that is at once deeply intellectual and deeply spiritual, acknowledging the possibility of infinity and the mystery that comes with it. So, what if this isn't all there is? Then our stars and galaxies are just one refrain in an endless cosmic song. Does that make them any less melodious? No. To us, they are everything, and they are precious. And if in addition, the choir of creation is larger and more complex than we knew, then there is even more reason to be filled with reverence and wonder. We close our eyes and imagine for a moment, countless universes shining like bubbles in a vast foam, or like an orchard of worlds stretching out beyond sight. We imagine each universe has its own sky, perhaps its own version of someone looking up and feeling small yet curious. In this grand symphony, we, in our universe, contribute our part. A small, clear voice in an unspeakably large choir. The song is one of existence, exploring all possibilities, and through science and storytelling, the cosmos, or multiverse, finds a way to know itself through our eyes and our understanding. Now we open our eyes again to the familiar stars above. They seem a little kinder now, as if winking at a secret we've shared. The night breeze is cool, carrying the earthy scent of our world, our dear world that nurtured us. For all this talk of other universes, it is here that we love and strive and wonder. Here is where we make our meaning. The multiverse has not answered the question of meaning for us. Instead, it has enriched the context in which we ask it. Meaning, it seems, is ours to create, in whatever corner of the multiverse we inhabit. We stand together under the cosmos, humbled by its vastness, yet uplifted by its possibilities. We feel small, but not insignificant, transient, but not pointless. We are part of something so much larger, and that realization does not diminish us. It ennobles us. It means the adventure of discovery will always continue. There will always be new horizons to explore, new questions to ask. Our universe was once unknown and mysterious, and we have made it familiar. If there are other universes, perhaps one day, in some form, they too will become part of the purview of understanding. Until then, we carry the torch of curiosity forward, illuminating what we can and respecting the darkness of what we cannot yet see. In the multiverse of ideas, we have voyaged through reflections and dreams, through mirrors, and branching streams of time. It's time now to gently return to our own world. We take one last, long look at the stars. The night is deep and silent. In that silence, there is a whisper of infinity. We sense the multiverse not as an abstruse theory, but almost as a presence, a silent chorus behind the curtain of reality, singing possibilities. And we, tiny though we are, sing along by simply living our lives and seeking truth. When dawn comes and the stars fade, we will go about our day, but perhaps with a renewed sense of wonder. Maybe we'll pause and think, the light of this morning sun could be rare in the multiverse. Let me feel its warmth with gratitude. The loved ones I speak to, the act of kindness I can do. In this universe at least, these matter immensely. The multiverse, if it exists, is not an escape from our reality, but a profound backdrop that can make our reality even more meaningful. As the first hint of morning glows at the horizon, we conclude our journey. We went seeking the multiverse and found that, whether or not it's truly out there, it has already expanded our minds. We end not with an answer, but with a feeling, the feeling of awe. Awe at the richness of the cosmos, awe at human ingenuity to even conceive of the multiverse, and awe at our own capacity to find meaning and connection in a possibly infinite expanse. Our story, the story of one universe awakening to the potential of many, becomes a kind of cosmic meditation. We step forward into the daylight, carrying this perspective with us quietly. The question, what if this isn't all there is, will continue to echo, inviting further exploration. And whenever we need to rekindle our sense of wonder, we know we can look up at the night sky, remember the grand vision of the multiverse, and feel that childlike spark again. In the face of eternity and infinity, we find not despair, but endless possibility. Our journey through the multiverse has been like traversing a hall of mirrors, each mirror reflecting a different face of reality. Now, back in our own mirror, our own universe, we smile, a small, knowing smile, because we glimpsed the hypothetical reflections and returned wiser. We carry within us the stories of myriad universes, and that makes the story of our universe all the more precious. In that spirit of appreciation and wonder, we conclude our exploration. The multiverse, real or not, has given us a gift, the gift of cosmic perspective. With it, we walk gently through our world, eyes open to the stars, hearts open to the unknown, and minds ready to embrace whatever truths the cosmos has yet to reveal. We are humbled, we are inspired, and above all, we are connected to each other, to our universe, and maybe, just maybe, to all universes. In the beginning, there was silence, a silence deeper than night, softer than a held breath. Nothing moved, for nothing yet existed that could move. No stars, no galaxies, not even the whisper of a breeze in the dark. In this primordial stillness, before light and time and form, there was only a pregnant pause, an infinite calm awaiting a spark. And then, in that void, something happened. A flash, a burst of unimaginable brightness, and the silence was broken. The universe was born in an eruption of light and energy, a silent explosion that rang with no sound, yet carried the promise of everything to come. From that moment, space unfurled like a new scroll, stretching, expanding, filling with the first hot glow of creation. Still, there was no ear to hear, no eye to see. All was energy and plasma and the slow birth of matter. Yet, as the cosmos burgeoned outward, the silence remained underneath the cosmic symphony, like a bass note holding all melodies, the backdrop of the vast expanding space. Eons passed in wordless majesty. Stars kindled across the darkness, clustered into galaxies, swirled into patterns by gravity's gentle but inexorable hand. Great structures formed, filaments of galaxies and voids larger than anything we can truly imagine. In all of this grandeur, in all the furnace roar of stars and the collisions of galaxies, a profound silence still reigned. It was not an empty silence, but a pregnant one, the silence of a universe in the making, as yet without anyone to witness it. Nebulae blossomed like cosmic flowers, stars lived and died, forging heavy elements in their hearts and scattering them into the void. Planets coalesced around distant suns. Perhaps on countless worlds, oceans pooled and gentle winds blew under alien skies. But for ages, no voice broke the silence, no mind yet asked a question. On one tiny planet, orbiting an ordinary star in an ordinary galaxy, something miraculous stirred. Life. In warm, shallow seas, simple microbes began to live, multiply, and evolve. The silent universe had given rise to tiny living things that could sense and respond. They knew nothing of the larger cosmos, only the immediate instinct to survive. But life grew more complex and daring. It crept onto land, took on myriad forms in oceans and forests. And in time, on that little blue world, consciousness sparked. Creatures emerged who could wonder. They looked up at the night sky with curious eyes. They felt small under the canopy of stars, yet compelled to reach out in thought. From their lips and hearts came the first question: what is all this? Where did it come from, and why? Thus, in a corner of the universe, the great silence birthed a question. It was perhaps the first time the cosmos had been asked to reflect on itself through the very beings made of its dust. In those early questions, uttered around flickering campfires or silently pondered under the wheeling stars, the universe itself found a voice. Through us, the cosmos began to speak and to ask. A strange paradox. Out of the universe's stillness grew minds that would not be still, that hungered to know. The night sky's grandeur made early humans feel both awe and mystery. They saw patterns in the stars and spun stories, sensing perhaps that the darkness was not empty, that there was something vast and eternal out there, beckoning. Who placed the stars in the sky? What lies beyond that glittering curtain? Is the universe around us all there is, or just a piece of something far greater? These questions, simple and profound, were the beginning of our journey. And they have no end. As though space itself were whispering to us, we felt an urge to explore, to seek the limits of what we can see. We learned to build tools, first telescopes of glass and metal, later great observatories, to extend our vision deeper into the silence. With each improvement of our cosmic eyes, the known universe grew. What once was a dome of twinkling lights became an ocean of stars, then countless galaxies, and then structures beyond galaxies. We discovered that the stars are not scattered randomly. They are gathered in immense cities of stars, the galaxies, each containing billions or trillions of suns. Our own Milky Way is one such city, a flat disk of light arcing across the sky. And beyond it, we found others. Andromeda, the whirlpool shapes of spirals, the blob-like ellipticals, the tiny dwarfs swarming around bigger ones. We realized the universe is composed of these galaxies scattered through space like handfuls of luminous sand tossed into the dark. Through patient observation, we determined the scale of our cosmic neighborhood. Light, that fastest of messengers, takes years to cross the gulfs between stars and millions of years to travel from one galaxy to another. We began to grasp that the lights in the sky were incredibly distant. The deepest images, taken with sensitive instruments, staring for days into what seemed like an empty patch of sky, revealed a staggering sight. Hundreds of galaxies in just a pinprick of darkness. It was like finding a shimmering city on what looked like a blank horizon. Everywhere we point our telescopes, if we look long enough, galaxies appear. The observable universe, the portion we can in principle see, contains at least 2 trillion galaxies, each with billions of stars. These numbers defy imagination. Even as we say them, do we truly understand? Each galaxy, an island of stars, perhaps with planets and wonders of its own, multiplied by trillions. The scale humbles us. We sit on a small planet orbiting one star among those countless, and we realize we are tiny. Our world is a mere grain of sand on an endless beach. As our knowledge expanded, so did our questions. We found that the universe has an edge, but not an edge in space like a wall or boundary we could touch. Rather, a limit in time and light. We call it the observable universe, the region from which light has had time to reach us since the universe began. There may be more beyond, much more, but it lies forever outside our view, hidden behind a horizon of light. Why can't we see beyond? Because the universe has a finite age, about 13.8 billion years since the Big Bang fireball ignited existence as we know it. Light from very distant regions simply hasn't had time to travel to us yet. Imagine being in a vast wilderness at night with a lantern. You see trees around you in the lantern's glow. Beyond a certain distance, the forest is dark, not because it ends there, but because the light hasn't reached those faraway trees. Our cosmic horizon is like that, a sphere of light around us, 46 billion light-years in radius, beyond which the universe fades into an unknowable darkness. And yes, that horizon's radius is larger than 13.8 billion light-years because space itself has been stretching all the while, carrying distant galaxies further out. We peer out to the edge of what we can see, and it appears like a foggy wall, not a solid barrier, but a limit of clarity. That fog is actually the afterglow of the Big Bang, the cosmic microwave background radiation, faint heat left from the time the universe was a hot, dense plasma. It's as far back as light can show us, a view of the universe when it was only about 380,000 years old, beyond which it was opaque. So here we stand, creatures of stardust and curiosity, staring at the cosmic horizon. We strain to see if beyond that faded glow of the primordial fireball, there might be more, perhaps endless galaxies receding into eternity. We suspect the universe doesn't simply end past what we can see. The evidence whispers that space likely continues far beyond our observational reach. The patterns of temperature in that cosmic afterglow are almost too smooth, too uniform, as if our observable patch is just a tiny piece of a much larger whole. If the cosmos ended just past our horizon, space would likely curve visibly or wrap strangely. Instead, all measurements indicate space is very nearly flat on the largest scales, with no detectable curvature as far as we can tell. This implies either the universe is infinite, stretching on without end, or so vast and curved so gently that we have not yet seen the bend. Most cosmologists lean toward the idea that it might be effectively infinite, or at least extremely large beyond comprehension. If that's true, our observable universe could be a mere grain in an infinite desert of universes. Think about that for a moment. Beyond the furthest galaxy we can see, there may be countless more galaxies, and beyond them more without edge. If space truly goes on forever, then somewhere out there, far beyond the reach of any telescope, other beings might gaze at their night sky and see a patch of galaxies that includes our Milky Way as just a faint smudge. Or perhaps they are so distant that even our whole observable universe is just a tiny part of their view. In an infinite cosmos, possibilities become certainties. Somewhere, the arrangements of matter must repeat. It boggles the mind, but in an infinite expanse, there could be another region so far away that it is identical to our own in content. Another patch of space with galaxies arranged just like ours. Another Earth with someone just like you, reading these very words. This isn't science fiction. It's a logical implication of infinity, although it's practically unobservable and forever beyond our interaction. The idea is dizzying and a bit unsettling, an infinity of other realities just out of reach. Yet it reminds us how limited our perspective is. We sit in our tiny bubble of space-time and see 93 billion light-years across. But that might be like looking through a keyhole and thinking that's the entire world. We simply don't know how far the grand stage extends. The true extent of the universe could be infinite, or the universe might eventually loop back on itself in a grand cosmic curve. like the surface of a sphere, but in 3 dimensions. If space is curved into a finite shape without a boundary, it's conceivable, though unlikely in light of current data, that if we traveled in one direction far enough, billions of light years, we might someday end up back where we started, coming up behind ourselves like a traveler circumnavigating a globe. Some scientists have even speculated about exotic shapes for space. One proposal imagined the universe's shape as a kind of dodecahedron, a 12-faced polyhedron, stitched together in a way that the cosmic microwave background might show repeating patterns. For a time, there were hints in the data, faint patterns that could suggest we were seeing the same regions of space in multiple directions, as if light had wrapped around the universe. But so far, these hints have not solidified into proof. The simplest explanation, flat and potentially infinite, remains most plausible. Yet the shape of the universe, its global geometry and topology, remains one of those great unanswered questions. Is the cosmos infinite or finite? Does it have an overall curvature or a unique topology beyond our horizon? We live suspended between possibilities, unable to step outside the universe to see it from the outside. Standing on the shores of the cosmic ocean, we realize that not only is there a limit to what we can see, but that the universe is astonishingly old and dynamic. The cosmos we observe is not eternal and unchanging. It has a history. The galaxies are flying apart, space itself stretching and carrying them away from each other. When we first discovered in the early 20th century that distant galaxies all seemed to be rushing away, it was as if the universe were breathing out, expanding. Rewinding this expansion with our calculations, we found it all converges back to that fiery beginning, the Big Bang. That was a revelation. Our universe had a birth in time. There was a moment, however brief, when all that we see and all that we cannot see was concentrated in an inconceivably hot, dense state. Before that, we do not know if before even exists in a meaningful sense, since time itself might have begun with the Big Bang. This origin story is derived from solid evidence: the expanding space, the cosmic background radiation, the mix of light elements. Yet it leaves us with profound mysteries. What ignited the Big Bang? What, if anything, came prior? Was it truly the beginning of everything, or just the beginning of our cycle of reality? We humans, naturally curious, push against the curtain of the unknown. We have conjectured many ideas for what set the stage for our universe. Some propose that our Big Bang might have been one of countless others. Perhaps the universe goes through cycles of birth, death, and rebirth, a bouncing cosmos that contracts and then explodes anew, over and over. Others imagine our universe budding off from a parent multiverse, a foam of bubble universes endlessly forming like bubbles in boiling water, each bubble a universe with possibly different properties. In such scenarios, the Big Bang was not the absolute beginning, but simply our bubble's local genesis. Still others invoke the idea of quantum fluctuations. Maybe nothingness is inherently unstable, and a tiny fluctuation could tunnel into creating an entire universe. Our cosmos could have sprung from a quantum event out of a vacuum of some higher reality. These ideas venture far beyond the realm of testable science, at least for now, but they arise naturally from our attempt to answer the question of origins. The truth is, we don't know what caused the Big Bang, or if that concept even makes sense in the absence of time. The very word cause assumes time already exists to allow an effect to follow, and if time began at the Big Bang, asking what came before might be as meaningless as asking what's north of the North Pole. Not knowing, however, does not stop the questions, it fertilizes them. Each mystery begets more wonder. We gaze at the observable universe, at that limit of perception, and wonder, if there are things forever beyond our sight, how can we ever know them? Perhaps we cannot, but we can infer hints. For example, our observable universe seems remarkably uniform in temperature in all directions. Even regions that are so far apart, light couldn't travel between them in the age of the universe to even out the heat. How did opposite ends of the sky agree on the same temperature without being in contact? To solve this puzzle, scientists proposed a radical idea: inflation. In the infant moments of the cosmos, a fraction of a second after the Big Bang, space itself might have blown up exponentially fast. An extreme expansion that took a tiny, uniform region and stretched it so vast that all we see now originated from that same patch. This would explain why distant parts of the sky have the same ancient heat signature. They were once close before inflation shoved them far apart. Inflation neatly accounts for some observed properties, suggesting our whole observable universe was once an infinitesimal speck. But inflation, if true, also dramatically broadens our perspective. That initial tiny region after inflation became huge, far larger than what we now observe, and inflation might not have been a one-time event that ended cleanly everywhere. Many inflation theories predict that inflation might be eternal, still occurring in far-flung regions, continually spawning new bubbles of space that themselves go on to expand and cool, becoming universes in their own right. In this picture, our universe is one bubble among a potentially infinite multiverse. Each bubble might have different physical conditions, different types of particles, even different dimensions or laws. We have no way, at present, to confirm the existence of other universes. They would be beyond our horizon, causally disconnected from us. Yet the theory that predicts them arose from trying to explain things we can see, lending some credence to the concept. The multiverse idea tickles the imagination. It suggests a reality far larger or more varied than anything we can directly detect. If true, the great silence beyond our cosmic horizon might be filled with other universes we will never know. A sobering and exhilarating possibility. Some of those universes could be barren, lifeless expanses where stars never formed. Others might be strange, with physics so alien that atoms as we know them can't exist. And perhaps some might be kindred to our own, with galaxies and stars, maybe even life. Of course, these speculations might forever remain philosophical musings. Without evidence, they remain in the realm of the unknown. But it is astonishing that human minds, products of a single universe, can even conceive of realities beyond it. Our imaginations press outward to the ultimate limits of existence, refusing to accept an end to the story. The cosmos, through us, is pondering what lies beyond itself. Yet, even as we dream of multiverses and infinite space, we must contend with enigmas right here in the observable universe. Mysteries woven into the fabric of the cosmos we see. In the late 20th century, as our instruments grew more precise, we encountered one of the most profound. We realized that we understand only a tiny fraction of the cosmic contents. All the stars, planets, galaxies, everything that shines, or that we can detect with any form of electromagnetic radiation, amount to a mere 4 to 5% of the total mass energy of the universe. The rest, the vast majority, is invisible to our eyes and instruments, yet its presence can be felt through gravity. This realization dawned gradually, starting with the way galaxies rotate. We expected, based on the gravity of visible stars and gas, that stars at a galaxy's outskirts would orbit more slowly, just as planets farther from the sun move more slowly, weakened by distance. But to our surprise, we observed that stars in the outer reaches of galaxies were moving just as fast as those closer in. It was as though some extra gravitational force was present, something we couldn't see, holding the outer stars in orbit and preventing them from flinging away. The same unseen influence showed itself in other ways. Clusters of galaxies, huge collections where hundreds of galaxies orbit a common center, were behaving as if they had far more mass than what our telescopes could account for. Light from distant galaxies was found to be distorted and magnified by massive invisible clouds, like a giant lens made of something transparent. All these clues pointed to one conclusion. An unknown form of matter permeates the universe, outweighing normal matter by a factor of about 5. We called it dark matter, not because it's dark like soot, but because it neither emits nor absorbs light. It's utterly invisible, detectable only by its gravity. What is dark matter? We still don't know. It could be some new kind of elementary particle that doesn't interact with light or normal atomic matter except through gravity. Perhaps faint, ghostly particles left over from the Big Bang that pass through Earth and through our bodies by the billions every second without a trace. Experiments deep underground and in particle accelerators are attempting to catch a glimpse of a dark matter particle. But so far, they've only placed limits on what it could be. It's humbling. We have this elegant theory of fundamental particles and forces, the Standard Model, that describes atoms and light and so much else, and yet it doesn't include a particle that can account for dark matter. So either there is physics beyond our current theories, a new particle, a supersymmetric partner, a hidden sector of forces, or, just possibly, our understanding of gravity on large scales might be incomplete, meaning what we attribute to unseen matter could be a subtle shift in how gravity works over vast distances. Most evidence favors actual dark matter substance, because the patterns are hard to explain with modifications of gravity alone. Dark matter is like a shadow universe overlain on the one we see. It formed a cosmic scaffolding in the early universe. Imagine an invisible web, filaments and knots of dark matter, and normal matter fell into its gravitational wells. This process seeded the formation of galaxies and clusters along the dark matter web. In a sense, the luminous structures we observe, galaxies, stars, planets, and us, are arranged on the template that dark matter provided. Yet we cannot directly behold this scaffolding. We map it indirectly by observing how it bends light, gravitational lensing, and how it influences the motions of galaxies. What an irony that most of the universe's mass is invisible to us. We are like fish swimming in water, yet not seeing the water, only sensing its currents. The dark matter neither shines nor bumps into atoms in a way we can easily measure. It whispers to us only through gravity, the subtlest of clues. We have given it a name. We hunt for it with detectors in deep mines and in the Large Hadron Collider. And perhaps one day we'll finally hear its voice. Until then, it remains a tantalizing mystery, a vast, unknown sea in which the islands of stars float. As if that weren't enough, an even stranger revelation awaited us. At the turn of the 21st century, astronomers painstakingly measuring the expansion rate of the universe made a shocking discovery. They expected to find that the expansion, slowed by gravity over time, was either coasting gently or perhaps starting to decelerate more strongly if the universe had a lot of matter. Instead, they found that the expansion isn't slowing at all, it's speeding up. The galaxies are not just rushing apart, they're accelerating away from each other, like a driver who, instead of coasting uphill, suddenly floors the gas pedal. This was the last thing anyone expected. Whatever could be causing this acceleration was not something we could see. It wasn't normal mass, which would attract, not repel. We named this mysterious phenomenon dark energy, a term that is a placeholder for our ignorance. Dark energy seems to make up about 70% of the total energy content of the cosmos, dwarfing even dark matter, which is 25%, leaving ordinary matter as a cosmic afterthought. What is dark energy? That question cuts to the core of our understanding of physics. One possibility is that dark energy is a property of space itself. In the equations of general relativity, Einstein's theory of gravity that describes how matter and energy tell space-time how to curve, there is a term, the cosmological constant, which Einstein once introduced and later retracted, thinking it unnecessary. This term corresponds to an inherent energy of empty space, an energy that doesn't dilute as space expands. If space has an innate energy, it would act like a sort of pressure or anti-gravity that pushes things apart. And indeed, this cosmological constant idea fits the observations fairly well, a constant energy density in space that started dominating the universe's dynamics a few billion years ago, causing expansion to accelerate. But why would such a constant exist? And why of that particular magnitude? When physicists try to calculate how much energy empty space should have, based on quantum theory, where even vacuum teems with virtual particles popping in and out, the theoretical value comes out enormously larger, a ghastly mismatch with what we observe. It's one of the worst disagreements between theory and observation ever encountered, signifying we deeply misunderstand something. So perhaps dark energy isn't a simple constant. Maybe it evolves, a dynamic field that changes over time, a concept dubbed quintessence after the fifth element of the ancients. Quintessence would be a new substance or field-filling space, one that can vary from place to place or era to era, and whose properties we have yet to determine. Another wild possibility: perhaps our understanding of gravity needs revision at the very largest scales. Maybe, like Newton's laws were superseded by Einstein's relativity might itself be a limiting case of a deeper theory that yields an accelerating cosmos without invoking a mysterious energy. For now, dark energy remains an enigma. It's as if we're children who notice that a top is spinning faster on the tabletop than it should, yet we can't see the hand twisting it. The universe's acceleration is a clue that our cosmic story has a twist, literally a speeding up, and we're in the dark, pun intended, about why. What we do know is that given this acceleration, the future is quite bleak for our view of the cosmos. If dark energy continues to push the expansion, distant galaxies will rush away faster and faster. Far in the future, beyond tens or hundreds of billions of years, other galaxies might recede so far and so fast that their light can no longer reach us. An observer in that far future might see an empty universe, just their own galaxy and nothing else, unaware that other galaxies ever existed. The thought that the rich cosmos we observe is a temporary gift of this epoch is poignant. We happen to live when the universe is young enough that galaxies are still in view. The accelerating expansion means the vast majority of galaxies are slipping beyond reach, like ships sailing over a horizon from which they'll never return. But why this is happening? Why now, and what exactly dark energy is? Those answers elude us. The silence regarding dark energy is profound. We can measure its effects with exquisite precision, yet the cause of those effects remains a whisper from the void. From the grandest scales of the expanding universe, let us turn inward to one of the most fearsome and fascinating objects nature allows: black holes. These are regions where matter has been crushed into such density that the fabric of space-time itself has curled in on itself, creating a pit from which nothing, not even light, can escape. A black hole forms, for example, when a massive star reaches the end of its life. The star's core collapses under its own weight, compressing beyond even atomic structure, beyond anything we can properly imagine, until it becomes an infinitely dense point, a singularity, wrapped in a spherical cloak of gravity. The boundary of that cloak is called the event horizon. Once you cross that threshold, there is no return. The concept of an event horizon is chilling and intriguing, a one-way membrane in the universe. Outside it, space and time behave normally. Inside, all paths inexorably lead down to the central singularity. It's a point of no return, a cosmic trapdoor. Black holes challenge our understanding of physics at a fundamental level. According to general relativity, the singularity at the center has infinite density and zero volume, a place where the known laws of physics break down completely. This signals that our theories are incomplete. Infinities in equations often mean we're pushing the theory beyond its domain of validity. We need a theory of quantum gravity, combining quantum mechanics with gravity, to fully describe what happens at those extreme densities. But we don't yet have that theory. So inside the black hole, hidden from our view by the horizon, nature keeps her deepest secret. It's as if the universe has places it refuses to show us, where it hides the answers to the final exam of physics. What would it be like to fall into a black hole? Imagine approaching a black hole in a spaceship. From a safe distance, it might actually be quite invisible unless it's feeding on surrounding matter, which can glow brilliantly as it heats up falling in. If it's a solitary black hole, you'd see stars behind it, warped into rings or arcs by its intense gravity, gravitational lensing. As you got closer, the pull on your ship would increase. If the black hole is of stellar mass, the gradient of gravity between your nose and tail is so steep, it would stretch you out in a process morbidly named spaghettification. You'd be torn apart before you even reached the horizon. But if it's a supermassive black hole, like the ones at galactic centers, millions of times the mass of the Sun, the tidal forces at the horizon might be mild, since the gravity, while strong, changes more gradually across your body. In that case, you could actually cross the event horizon without immediate destruction, and perhaps without even noticing crossing it, since nothing particularly physical marks that boundary aside from the point of no return property. Once inside, however, all paths lead to the center. Your engines, no matter how powerful, cannot reverse course. Time and space trade roles in a sense. Just as you cannot stop moving forward in time, now you cannot stop moving toward the singularity. According to classical relativity, within a short time, you reach the central singularity and are crushed. Your mass adds to the black hole, your identity lost. But physical intuition rebels. Is information truly destroyed in a black hole? Quantum theory says information about a system's state cannot be lost. At least, that's a principle of quantum mechanics as we understand it. If a black hole simply eats things and then evaporates, we suspect black holes slowly evaporate via Hawking radiation, a faint glow due to quantum effects at the horizon. What happens to the information that fell in? Hawking radiation, as originally conceived, carries no information. It's like heat radiating from a warm object, basically random. If a black hole completely evaporates away, does the information of everything it consumed just vanish from existence? That possibility horrified physicists, as it seemed to violate a sacred tenet of physics: information conservation. This is the famous black hole information paradox. Some think the information is encoded in subtle correlations in the Hawking radiation, so that in principle, if you capture all the radiation, you could reconstruct what fell in. Others have proposed exotic solutions. Perhaps the singularity isn't the ultimate end. Maybe it somehow connects to a new region of space-time, a budding universe or a white hole, theoretical time-reversed black hole that spits matter out. Some suggest that what we call singularity might be a mischaracterization, and quantum gravity, when understood, will show no infinite crunch, but something like a bounce or a portal. Yet others imagine that black holes might have firewalls at the horizon, blistering zones of quantum energy that destroy information before it even reaches the singularity, thus preserving quantum rules, but at the cost of violating Einstein's predictions of a smooth passage through the horizon. We just don't know the answer yet. Astonishingly, what was once theoretical musing, we have now seen. In recent years, humanity managed to capture an image, via radio telescopes arrayed across Earth, of a black hole's shadow, essentially the silhouette of the event horizon against the backdrop of hot plasma around it. The first such image, of the supermassive black hole in the galaxy M87, showed a fuzzy donut of light, just as predicted by general relativity. We have also measured gravitational waves, ripples in space-time itself, from black holes colliding, hearing the literal ringing of space-time as they merge. These observations confirm that black holes are real, not just mathematical quirks. They exist in the universe by the dozens, likely by the millions. Our own Milky Way harbors a giant black hole at its core, over 4 million times the mass of the Sun. Stars orbit this invisible monster like comets around a phantom sun. And nearly every galaxy likely has one, with masses from millions to billions of solar masses, shaping the evolution of their host galaxies in ways we're still investigating. So black holes stand as both a triumph of understanding — we predicted them, then observed them — and a frontier of mystery. Their insides remain terra incognita. They force the question of how the very large, gravity and space-time, and the very small, quantum particles, mesh together. To truly know what a singularity is, or what happens at that boundary of physics, we will need a unified theory that marries quantum mechanics with general relativity. It's often said that at a black hole's center, the equations of general relativity yield infinity, meaning the theory throws up its hands. It's as if at that point, the universe is saying, "Here, your current understanding halts. A new understanding must begin." In the same vein, consider the nature of time itself, another profound mystery at the intersection of physics and philosophy. Time is something we all experience intimately, yet when we scrutinize it, it becomes elusive. We feel time flow. Every moment, we sense the now moving inexorably to the next now. We remember a fixed past. We anticipate an unknown future, and we seem trapped in this ever-moving present. But what is time? Physics treats time as a dimension much like space. In relativity, time and space are intertwined as space-time. Just as we can move north-south or east-west, we also move forward in time. But why do we only move in one direction in time, whereas in space, we can turn around? Why is yesterday set in stone and tomorrow so contingent? This one-wayness is called the arrow of time, and it appears most strongly when we consider entropy, the measure of disorder. The second law of thermodynamics says entropy in an isolated system tends to increase. Eggs scramble, but they don't spontaneously unscramble. Smoke disperses from a fire, but never gathers itself back into logs. In short, things tend to move from order to disorder, from concentrated energy to spread out energy. This provides a kind of arrow from a past of lower entropy to a future of higher entropy. Our memories and records are traces of lower entropy states. Perhaps the reason we remember the past and not the future is simply that the past is embedded in those ordered traces, like photographs, fossils, neurons in our brain, whereas the future hasn't left any traces yet. In this view, the arrow of time is a brute fact about initial conditions. The universe started in a very low entropy, highly ordered state. The Big Bang, despite being hot and dense, was actually very uniform, which is a kind of order. As the universe evolves, entropy increases. Stars burn fuel and produce heat, matter clumps and then energy dissipates, etc., thus giving time a direction. But this explanation, while broadly accepted, just pushes the mystery back one step. Why was the entropy low to begin with? Why was the early universe so orderly, laying the groundwork for an arrow of time that would later allow life and memory? We don't know. It might be a fortunate accident, or it might hint at deeper cosmological structure. For instance, in some multiverse scenarios, maybe new universes always start fresh with low entropy as they pinch off, and we naturally find ourselves in one of those. Another puzzle. At the microscopic level, the fundamental laws of physics, ignoring a subtle detail with certain particle decays, are mostly time-symmetric. They don't care if time runs forward or backward. If you filmed two particles scattering off each other and ran the movie backwards, you'd see a perfectly valid physical process. Yet at the human scale, time's asymmetry is obvious. How do those reconcile? The prevailing view is that the asymmetry isn't in the underlying laws, but in the boundary conditions. Again, that low entropy past. Thus, the flow of time might be emergent, not fundamental. Some scientists even propose that time as we perceive it, a flowing river, is an illusion, a byproduct of our consciousness stringing together events, whereas in reality, all moments might coexist in a block universe. In that block universe picture, the past, present, and future are all equally real, just different coordinates in space-time. And it's only our particular perspective, like a spotlight moving along the timeline, that gives a sense of flow. This interpretation is mind-bending because it means now is not a universal truth, but a subjective one linked to each observer. Relativity already showed that simultaneity is relative. Two events that are simultaneous for you might not be for me if we're moving differently. So in a deep sense, the notion of a global present is tricky. Is time perhaps an emergent phenomenon from something deeper, like entanglement or quantum states. Some cutting-edge ideas suggest time might arise from quantum entanglement patterns, or that our universe's time dimension could have sprung forth from a timeless quantum reality when certain conditions were met. These remain speculative, but they remind us that something as fundamental as time is still not fully understood. Time is at once the most familiar thing and the greatest mystery. We live in time. We cannot step outside it to examine it objectively. That's akin to asking a fish to describe water. It's so ubiquitous that it becomes elusive. We mark time's passage with clocks and calendars, but what we're really measuring is change relative to other change. A second is defined in physics by a certain number of oscillations of a cesium atom's radiation, for example. So time is tied to processes. If nothing changed, would time have meaning? In the vast stillness before the universe, if such a state can even be contemplated, what was time? Or did time begin when change began? The silence of the cosmos extends into the subatomic world as well, where our everyday intuitions falter. Peering into the quantum realm, we found uncertainty and paradox. The building blocks of reality, electrons, photons, and other quantum particles, do not behave like little billiard balls following neat paths. Instead, they exist as fuzzy clouds of possibility, described by a wave function that tells us only the probability of finding them in a particular state. It's as if, at a fundamental level, nature doesn't decide on an outcome until something forces its hand, namely, an observation or interaction that makes the potential become specific. This is encapsulated in Heisenberg's uncertainty principle. One cannot precisely know certain pairs of properties, like position and momentum, at the same time. If you pinpoint a particle's location, its momentum becomes uncertain. If you know its momentum exactly, its location smears out. Nature, it seems, imposes a fundamental limit on how much we can know, or perhaps on how much is decided, even in principle. This isn't a limit of technology, but of principle. It's as though the universe, at fine scales, refuses to give a straight answer, offering instead a spread of possibilities. Consider the famous double-slit experiment. When we send electrons or photons one by one through two narrow slits to a screen, an interference pattern emerges, as if each electron were a wave that went through both slits and interfered with itself. Yet, when we put detectors to see which slit the electron actually went through, the interference disappears. The electron acts like a particle that went through one slit or the other, not both. It's as if the electron exists in a ghostly blend of possibilities, both paths, until we look, and then it chooses one path, retroactively making itself a particle that had gone that way all along. This kind of behavior defies our classical logic, and the universe stays mum on how or why it happens. Various interpretations of quantum mechanics try to make sense of it. Some say the wave function collapse is just fundamental and random. Others propose that each possible outcome actually branches off into a separate reality. The many worlds interpretation, where the electron went through left slit in one branch and right slit in another, and these two branches do not interfere once decoherence, entanglement with environment, has happened. Many worlds offers a wild vision. Every quantum event spawns a new universe, so there is an ever-branching multiverse of possibilities. If true, then at this very moment, innumerable versions of reality are splitting off for every quantum choice. In some, you took a breath a second later than in others. In some, a butterfly flapped its wings, whereas in others it stayed still, and those small differences proliferate. This would be a multiverse of a different kind, not separated by vast distances, but coexisting on top of each other in a higher dimensional quantum space, splitting at each interaction. It's a solution to making quantum mechanics purely deterministic. No randomness, just every outcome happens in some branch. But it means that reality is unimaginably more complex than we perceive. Yet from within one branch, we can never communicate with the others.
So how could we ever tell if this is true? The cosmos yields phenomena that invite such bizarre explanations, and then remains silent, leaving us to debate and wonder. Another perplexing quantum phenomenon is entanglement, what Einstein famously called spooky action at a distance. When two particles are entangled, they share a single quantum state. If you separate them across the galaxy and then measure one, instantly the other is affected, or rather, instantly you discover that the outcome on one side is perfectly correlated with the outcome on the other side, as if they were connected. For example, two photons can be entangled in polarization, such that if one is measured to be vertically polarized, the other will always be found horizontally polarized, say the opposite, no matter the distance. It's not that one sends a signal to the other at measurement. As far as we can tell, nothing travels between them, and indeed, if you try to use this for communication, it fails. You can't actually send a message this way. Instead, it's as if the two particles are a single entity described by one combined wave function, and when you collapse it by measuring one, you simultaneously collapse the whole system. This is deeply counterintuitive. It implies the universe has non-local qualities. Parts of the universe far apart can be intimately linked in ways that transcend ordinary space and time relationships. Experiments have confirmed entanglement again and again. It's real. We even have technologies exploiting it, quantum cryptography, for instance. But why the universe allows this deep connectedness, how it fits with our concept of locality, and what it means about the underlying reality, remains mysterious. Some thinkers speculate that perhaps space and time themselves are not fundamental, and entanglement hints at a more basic fabric of reality from which space emerges. Picture that what's fundamental is information or relationships, and what we perceive as space is just a way of organizing those relationships for our macro understanding. In such a view, two entangled particles might be adjacent in the deeper reality, even though in our three-dimensional space they are far apart. Thus their coordination is instantaneous because distance is irrelevant in the underlying layer. This is speculative, but it's an attempt to make sense of what nature is quietly demonstrating to us without explanation. The silence of the quantum world, the lack of an intuitive story from nature about what's really happening, has haunted physicists and philosophers for a century. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." It's a humbling admission that even our best theory, confirmed by experiment to astonishing precision, is something we can use, mathematically, but not fully comprehend in plain language. Is the electron a particle or a wave? The only honest answer, it's something quantum, which has aspects of both, and depending on how we interact with it, it will manifest one aspect or another. It's as if reality at base is described not by the solid objects of our sensory experience, but by ghostly probability clouds and interconnections that defy straightforward description. We've developed a comfortable routine with quantum mechanics. Shut up and calculate, some say. Yet the human spirit itches to truly know, to have a picture, a narrative, something that feels resolved. And so far, the cosmos offers none. Perhaps one day a deeper theory, like a successful quantum gravity theory or a theory of everything, will unify these pictures and give us a new paradigm that makes quantum weirdness feel as natural as sunrise. Until then, we live with a fundamental not knowing at the heart of physics. Our journey through the unknown wouldn't be complete without reflecting on the mysteries that hit closest to home. We've looked outward to the edge of the universe and inward to subatomic realms. But what about life? What about consciousness? These are aspects of the cosmos too. After all, we are part of the universe, made of the same particles and subject to the same laws. In the cosmic perspective, life is a recent phenomenon, blossoming on at least one small world. But is it unique to Earth or common as starlight? This is one of humanity's oldest questions. Are we alone? The Earth teems with life in astonishing variety and tenacity. We find life flourishing in boiling hot vents at the ocean floor, in acidic lakes, in the frozen Antarctic permafrost, and high in the atmosphere. Life, once it gains a foothold, is hardy and adaptive. This gives us hope that life could exist beyond Earth, in niches we once thought too extreme, perhaps in the subsurface oceans of icy moons like Europa or Enceladus, or in the cloud decks of Venus, or on planets orbiting distant stars. We have now discovered thousands of exoplanets, planets around other suns. Some of these are in the so-called habitable zone, where temperatures might allow liquid water. A few are near Earth size and could be rocky. The sheer number of planets in our galaxy is staggering, likely on the order of 100 billion, roughly one per star on average, and many stars have multiple planets. With billions of galaxies, the number of planets in the observable universe might be more than all the grains of sand on all Earth's beaches. If even a small fraction of those planets are habitable, the number of living worlds could be enormous. And yet, we have not heard a peep. The universe, as far as our searches have detected, is quiet about life beyond Earth. No radio signals from alien civilizations beam through the sky, despite our listening via SETI for decades. No unmistakable technological signatures or visits, despite UFO lore. There's no confirmed evidence of extraterrestrial craft. We see no obvious ruins on Mars or elsewhere in the solar system. This great silence is puzzling. It's termed the Fermi paradox. Given the vastness of the cosmos, and presumably many opportunities for life, why have we not encountered anyone or anything? Where is everybody? Enrico Fermi famously asked. There are many possible answers, none confirmed. Maybe life is common, but intelligent life is exceedingly rare. Perhaps simple microbes abound on many worlds, in the oceans under ice crusts of moons, or beneath the soils of exoplanets. But the evolution of complex multicellular life, and then technological intelligence, is an extremely improbable chain of events. After all, for most of Earth's history, billions of years, life remained single-celled. Only in the last 500 million years did complex organisms proliferate, and only in the last few million did a species arise with intelligence capable of radio telescopes and rockets. Perhaps in many biospheres that step never occurs. Life stays microbial or animalistic, never building cities or machines. Or maybe civilizations do emerge on many planets, but they tend to have short lifespans. They might self-destruct via warfare or environmental collapse. Or perhaps they inevitably transition to some other state, like a virtual reality existence, and lose interest in communicating with the stars. It could even be that a galaxy teems with life and intelligence, but it's largely quiet and inward-looking, and the distances are so vast that communication is difficult. Signals might be rare, or we might not recognize them. Perhaps advanced beings use communication methods we haven't discovered, or maybe they abide by a cosmic etiquette, a prime directive, of not interfering with emerging civilizations like ours. It's also possible we are alone, or at least incredibly rare. Maybe life itself is a freak occurrence, needing such a special convergence of circumstances that Earth might be one of only a handful of places in the whole galaxy or beyond where it happened. Some scientists have suggested that certain unlikely events, like the origin of life from chemistry, or the jump from single cells to complex organisms, or the development of intelligence, might be low-probability flukes. If so, the universe could be mostly sterile, with us as a precious exception, or one of very few. That thought is both exhilarating, we're special, and terrifying, so fragile in the cosmic darkness. If we are rare or alone, it puts a huge responsibility on us to survive, to cherish life, to perhaps spread it. We are searching avidly for answers. Our robots crawl on Mars, drilling into rocks to find traces of past microbes. Our probes have sampled the plumes of Enceladus, shooting water from its subsurface ocean into space, and found organic molecules, tantalizing, though not proof of biology. We're designing missions to Europa and other worlds. And from Earth, or Earth orbit, we are beginning to peek at exoplanet atmospheres. We've detected atmospheres on a few distant planets, And soon, next-generation telescopes will try to find signatures of life. For example, an atmosphere rich in oxygen, which on Earth is maintained by life, or weird combinations of gases that scream metabolism at work. It's a challenging task. Exoplanets are tiny and drowned out by their bright stars. But the endeavor is underway. Perhaps in the coming decades or centuries, we'll get our first hint that biology is not unique to Earth. Imagine the day we detect, say, methane and oxygen and water vapor on an Earth-sized planet around a distant star, a combination hard to sustain without life. We will not hear aliens say hello, but we might finally know that the cosmic loneliness is an illusion, that life has filled other ponds in the great rain of creation. Until then, we have only questions and the emptiness between the stars. We've sent out our own signals, radio waves that have leaked from our transmitters for a century, spreading out as a faint bubble, 100 light years in radius. And we've deliberately beamed a few focused messages or carried plaques and golden records on spacecraft like the Voyagers. Those artifacts drift now in the interstellar void, likely to wander for millions of years. Perhaps one day, far future, some alien hand, or appendage or machine, will find our little bottles in the cosmic ocean and know that we existed. But for now, the only confirmed life in the universe that we know of is here, on this pale blue dot. That is a sobering truth. It means every living thing we have ever known, every experience of love, joy, struggle, discovery, all of it, has occurred in a thin film of life on one planet's surface. Life is a delicate chemical flame fighting entropy, and Earth is the oasis that nurtures it in our solar system. This knowledge urges us to protect our world, for if life is rare, losing Earth's biosphere would be an unspeakable tragedy. And if life is common, well, then we have friends yet to meet, and we should keep our planet thriving so that one day we might join a galactic community. Either way, the quest to know if we are alone goes on, intertwined with our own future. And then there is consciousness, the most immediate reality to each of us. For what could be more certain than our own awareness? Yet perhaps the hardest phenomenon to explain in scientific terms. Somehow, in the 13.8 billion year journey from the Big Bang's fire to now, the universe has developed the ability to contemplate itself. Hydrogen atoms coalesced into stars. Stars forged heavier elements. Those elements made planets. On one planet, chemistry begat life. Life grew brains, and now those brains contain minds that experience, question, and create. It sounds like a fairy tale, inert matter becoming sentient, yet it happened. In us, and likely in other creatures too, to varying degrees. Surely many animals are conscious in their own ways, though we humans possess a self-reflective awareness and intellect that sets us somewhat apart. How does mere matter give rise to the feeling of being? How does a collection of neurons, exchanging electrochemical signals, produce the redness of a rose, the taste of chocolate, the pang of sadness, the sense of self? This is often called the hard problem of consciousness, because explaining how the brain processes information, responds to stimuli, or controls the body, the easy problems. Those are difficult, but we can see how to approach them scientifically. But explaining why those processes should be accompanied by an inner subjective experience, why there is something it is like to be you from the inside, that's a different matter. We might map every neuron in your brain and track every spike and chemical, and still be left wondering at what point those physical events create a conscious experience. If a computer simulated your brain perfectly, would that simulation be conscious? Or is there something more than computation needed? Science, by design, deals with third-person observations, measurements of things from the outside. Consciousness is inherently first-person. It's the one thing you can't directly observe about me, nor I about you. I can tell you I feel pain or joy, and you can correlate it with brain activity or behavior, but the feeling itself is private. This gap between objective and subjective has led to philosophical standoffs for centuries. Mind-body problem, dualism versus physicalism, etc. The prevalent scientific view is that consciousness arises from brain activity, that the brain is the generator, or at least the transmitter, of the mind. If so, then consciousness should be explainable in terms of neurons and their interactions, but we haven't cracked how. There are intriguing leads. Certain brain processes correlate strongly with conscious states. For instance, synchronized oscillations in certain frequencies, or specific circuit loops in the cortex and thalamus. The Integrated Information Theory, IIT, suggests that consciousness corresponds to the amount of integrated information a system possesses, a measure noted as FEF. Under IIT, even a simple system might have a tiny bit of consciousness if it has a feedback structure that integrates information. So even a thermostat might have a minuscule glimmer of experience, which is a panpsychist kind of implication. Another theory, Global Workspace Theory, GWT, posits that consciousness is like a global blackboard in the brain, where information gets broadcast to many subsystems. What we experience consciously is the stuff that made it into this global workspace. These theories provide models and prediction, but none yet explains why the global workspace feels like something, or why integrated information should result in an inner life. Some thinkers have ventured that consciousness might be a fundamental property of the universe, like mass or charge, an idea known as panpsychism, the notion that perhaps all matter has some degree of consciousness, and complex systems like brains just amplify or collect it into the vivid awareness we know. This is not a mainstream scientific view, but it arises from the difficulty of explaining consciousness purely as emerging from non-conscious parts. If electrons and neurons are totally devoid of experience, how do a trillion of them together produce experience? Panpsychism answers, maybe electrons, and all particles, have extremely rudimentary proto-consciousness, some intrinsic aspect that is mental, and when arranged in complex ways, these form higher consciousness. It's a wild idea, harking back to ancient philosophies that saw spirit in all things. Whether true or not, it underlines how desperate the attempt to solve consciousness has become, that even such ideas get consideration. Alternatively, maybe consciousness is an emergent phenomenon that will eventually be explained in terms of information processing, but we just haven't found the right concepts yet. After all, concepts like temperature and pressure were once mysterious. How does the jostling of atoms create the feeling of warmth? But kinetic theory explained them. Perhaps one day we'll likewise demystify conscious experience, showing how certain patterns of computation just are the subjective feeling from the inside, similar to how a certain frequency of air vibrations just is the subjective experience of a musical note to an ear and brain. Some neuroscientists suggest that if you had a matrix of interconnected neurons or artificial units replicating the brain's structure, an inner life might spontaneously light up. But verifying that will be tricky, again, because we can't directly measure the consciousness, only infer it from behavior or reported experiences. For now, consciousness stands as an open question that straddles science, philosophy, and even spirituality. The cosmos has produced self-aware beings. We know this because we are them. But we don't understand the spark that lights up our thoughts. We don't know at what point in evolution consciousness arose. Do fish feel? Do insects? What about single-celled organisms responding to stimuli? Is there a faint glimmer of something it is like to be an amoeba? Does consciousness require a brain, or could an alien form of life, like a network of fungi or even a sufficiently complex machine, be conscious? Could the universe itself be conscious in some way, as some mystics and even a few scientists muse? Not in a simplistic anthropomorphic way, but in a sense that there is a level of awareness associated with the cosmos as a whole or with fundamental fields? These questions drift at the edges of empiricism. They may not all be answerable, at least not by traditional experiments, yet they matter to us because consciousness is the lens through which we experience everything else. Without it, we aren't even there to ask the questions. Let us step back now and look at the tapestry of what we know and what we don't know. The cosmos began, as far as we can tell, in silence and mystery, and that mystery remains at every level we probe. We have learned so much: the age of the universe, the recipe of elements, the existence of cells and DNA, the laws of gravity and electromagnetism, the reality of quantum fields, the genealogy of stars and galaxies, the expansion of space, the evolution of life. Our knowledge has blossomed, an impressive collective achievement for a species of former cave dwellers. And yet, what we don't know overshadows the patch of light we've kindled. The volume of ignorance is an ocean around our island of understanding. It humbles us, but it also excites and motivates us. Each generation has pushed further into that ocean. We often find that answering one question opens several new ones. We learned how stars shine, but that led to questions about stellar evolution and supernova. We discovered other galaxies, but that raised questions about dark matter to explain their motions. We uncovered the expanding universe, which posed the question of what the fate of expansion is and introduced dark energy. We deciphered the code of life, DNA, but then faced the complexity of how genes lead to consciousness. It's like climbing a mountain. Each time you reach a summit, you find a higher peak beyond. Far from being disheartening, this is invigorating. It means the adventure continues, perhaps forever. Consider the nature of space itself. At first glance, space seems like nothing, an empty void, the backdrop for matter. But we've come to see space as something with structure and activity. Einstein's relativity showed that space and time can stretch, bend, and ripple. Gravity, in that theory, isn't a force emanating through space. It is the shape of space and time itself, curved by mass and energy. When you put a heavy object like the sun in space, it dimples the space-time fabric around it, and the Earth orbiting the sun is like a ball rolling around a dent, following curves in space-time. This was a radical shift. Space is not just an inert stage, it's a dynamic actor. Then quantum physics adds another layer. Even a perfect vacuum, completely devoid of particles, isn't truly empty. It seethes with ephemeral phenomena, quantum foam, as some call it. Particles and antiparticles can briefly appear and annihilate. Fields fluctuate constantly at microscopic scales. There is a constant jitter in the vacuum, so much so that the vacuum, paradoxically, contains immense energy if summed, though our inability to tap or see most of that energy is another puzzle. These vacuum fluctuations have real effects. They cause tiny, measurable forces. The Casimir effect, where two close plates have a slight attraction due to altered vacuum modes between them, and contribute to phenomena like the Lamb shift in atomic physics. So the nothingness of space is actually a roiling, boiling brew of potential, the foundation upon which everything rests. Space itself might undergo phase transitions. Some cosmologists speculate that in the very early universe, space was in a different state, with different symmetry between forces, and as it cooled, it crystallized into the form we know, possibly releasing energy that drove inflation. The vacuum today might hide exotic fields, like the Higgs field, which pervades space and gives particles mass, discovered experimentally in 2012. A tangible example that space contains fields with constant values. Dark energy could be the energy of space's vacuum. If space has energy, then a volume of vacuum isn't truly nothing. It's more like a latent something. We're reminded of a line from a poet or sage that silence is not empty, it's full of answers. Similarly, space is not empty. It's full of the answers to questions we've yet to formulate. Yet for all that, when you stand outside on a clear night and look up, space feels like an immense, silent void between the stars. That serene emptiness cradles all of creation. It separates and connects everything. Every breath you take, the molecules were at one time scattered in space before the Earth formed. And after you exhale, given enough time, they may escape Earth and wander the galaxy. Space allows that movement. Space, by its vastness, also ensures that objects can exist without immediately colliding with one another. It grants stability to solar systems and galaxies by giving them room. But is space infinite? Does it go on forever? We addressed that earlier. We're not sure. If it is finite, what lies beyond? Perhaps nothing we can comprehend. Or perhaps our three-dimensional space is embedded in a higher dimensional reality. String theory suggests extra spatial dimensions we don't perceive, perhaps curled up small. Could it be that our space is like the surface of a balloon, and there is a higher dimensional space outside it? If so, that's outside our experience, and possibly forever inaccessible. Or maybe beyond all galaxies, beyond the cosmic horizon, space just continues, with more galaxies ad infinitum. So even space, the very fabric we exist in, holds mysteries. Some researchers think space and time might be emergent from something more fundamental, like quantum entanglement patterns or spin networks in theories of quantum gravity. Imagine if space-time is not the base level of reality, but a kind of approximate large-scale picture that arises from microscopic physics that isn't in space-time at all. This is speculative, but we already have hints that space and time break down at extremely small scales. The Planck scale, around 10 or 35 meters. At that scale, quantum foam might be so wild that the notion of a smooth space-time becomes meaningless. Space might be chunky or erratic, full of baby black holes popping in and out, wormhole connections blinking open and shut, a true quantum chaos. We have no microscope to see that deep. It's far beyond our current or foreseeable technology to probe distances that small directly. But mathematical attempts at quantum gravity, like loop quantum gravity or aspects of string theory, suggest space-time could have an atomic or quantum structure. If so, then asking about the continuity of space or the absolute beginning of time might be like asking where exactly a flowing river ends when it fans into a delta. Up close, the distinctions blur. We cannot now answer if time had a beginning, or if space has an edge, or what space is made of, if anything. But we can marvel at the fact that we, ephemeral beings made of cosmic bits, can even frame such questions. Think of the journey, from silent stillness to swirling galaxies, to starshine on primordial Earth, to life evolving in the oceans, to human minds reaching out with curiosity. We are a way for the universe to know itself. That poetic insight appears literally true. Our senses, our instruments, extend the universe's ability to perceive. Without conscious observers, would the majesty of the cosmos have any meaning? The galaxies would still dance, the stars would still burn, but there would be no appreciation, no insight, no knowledge. Through us, and maybe through other conscious creatures out there, if they exist, the universe gains the gift of self-awareness. We are the cosmos made conscious, and so we are a small part of the cosmos, looking back at itself and trying to understand. It's as if the universe has sprinkled seeds of awareness within itself, and those seeds, in the form of beings like us, awaken and stare out in wonder, asking questions. We ask about the Big Bang and black holes and quantum foam, but in a sense, the universe is asking those questions through us. Space itself speaks in our questions. The great silence of outer space finds a voice when a scientist in a lab theorizes or an artist at night paints the Milky Way. We feel the mystery and we respond with curiosity, a fundamentally human trait. Perhaps a fundamental cosmic trait expressed through humanity. Where do we go from here? The unknowns beckon us forward. We will keep building better eyes. telescopes to hunt for exoplanet atmospheres, to watch the birth of stars, to glimpse the first galaxies forming not long after the Big Bang. We will keep listening for signs of life or intelligence beyond Earth, refining our methods, maybe sending new messages or probes to nearby stars. We'll continue to smash particles together or devise clever detectors deep underground, hoping to catch whispers of dark matter or new physics. We'll push quantum theory to its limits, perhaps eventually developing quantum computers that might simulate aspects of reality we couldn't before, giving insight into those mysteries. Perhaps one day we'll integrate gravity and quantum mechanics into a single, coherent theory, a momentous achievement that could answer some of those questions, maybe revealing what really happens at a singularity or exactly how space-time emerges. And as we do, new questions will arise. Perhaps solving dark matter and dark energy will lead us to other puzzling phenomena. Perhaps understanding consciousness will open entire new realms of science about subjective experience. There's also a chance that some mysteries remain mysteries, either because they are fundamentally beyond our cognitive reach, or because obtaining the evidence is practically impossible, like a multiverse beyond contact, or what before the Big Bang was, if that concept even applies. But even then, exploring these ideas can enrich us. They make us grapple with the limits of knowledge, with the meaning of reality.
Throughout all this, one truth remains. To not know is not a failing, but a feature of our existence. If we knew everything, the universe would lose its allure, its dynamism. Each of us in life starts not knowing, then learns, and in learning, discovers more things we don't know. A child might gaze at the sky and not even know what stars are. Later they learn, but then new layers of mystery unfold. What are stars made of? How did they form? The questions grow with the answers. This is the engine of discovery. Our ignorance is vast, but it is the dark canvas on which we paint our understanding. Imagine if every answer were handed to us complete. We'd have knowledge, but no journey, no adventure. It is the chase, the pursuit of truth, that often gives us purpose and joy. The moment of revelation, eureka, is sweet, but it is earned by the long not knowing that came before. And so, even as we strive for answers, we can find peace and wonder in the open questions. The cosmic mystery isn't something to be sad about. It's something to celebrate. It means we are intimately connected to a universe that is richer and more profound than our current imagination. It means there will always be new horizons to seek, new truths to uncover, or at least ponder. Picture yourself under the night sky again, as in the beginning. The stillness of the air, the silent twinkling of ancient starlight. You feel the immensity above and around you. In that moment, you are aware of a grand ignorance. You don't know what all is out there, or why it exists, or if someone might be looking back. Yet you are also aware of a profound connection. You are made of this universe's elements, your bones calcium from long-dead stars, your blood carrying iron forged in supernovae. The very act of you wondering ties you to the cosmos. Your questions are like a bridge between your mind and the infinite. Yes, the void is silent, but in our minds, that silence begets a quest. We fill the quiet with our inquiries and our explorations. We send out spacecraft, like extending our senses to the planets and beyond. We smash particles to glimpse creation's most microscopic secrets. We invent mathematics to describe black holes and quantum waves. We contemplate philosophical implications of time and existence. These are our conversations with the cosmos, and though it may not answer in words, it answers in wonders. We find one day a new kind of particle, or see a new kind of galaxy, or decode a new signal, and that is the universe's reply, telling us a little more of its story. Perhaps the universe also answers through our own self-discovery. The more we learn about nature out there, the more we reflect on ourselves. We realize how precious life is, seeing how hostile most of space can be. We see Earth from space, a pale blue dot, and it triggers a global awareness of unity and fragility. We understand that we are but one species among many, on one planet among many, in one galaxy among billions. This perspective can evoke humility and also a sense of fellowship with all existence. In cosmic timescales, human civilization is just a blink and an individual life not even a flicker of a star. But to us, our lives are everything. They are our personal universe of experience. The big cosmic mysteries often reflect in microcosm in our personal mysteries. We wonder what our purpose is, how our minds work, how to find meaning in the vastness. And the answers are not handed to us. Each person, in a way, lives their own questions and gradually, hopefully, lives into answers. In that, we mirror the cosmos. Each of us begins in the darkness of not knowing, and along the way, we gather light. The process is continuous and perhaps infinite. In the end, after traversing all these wonders, from the birth of the universe to the nature of space, from dark matter to consciousness, we come back to a simple human truth. To not know is to be alive. Our ignorance is not just an absence. It is the driving force that keeps us searching, learning, striving. As long as there are things we don't know, we wake up in the morning with curiosity burning in our hearts. As long as mysteries abound, we have reason to marvel and reason to push boundaries. Imagine a final theory of everything that answers all possible scientific questions. Would curiosity die? Perhaps it would shift inward or to new realms, like creating art or simulated universes. But as long as we retain any sense of wonder, we find new questions. Even if somehow we understood the entire physical workings of the cosmos, we might still ask, why is there something rather than nothing? Or, what is the ultimate meaning of it all? Those questions might never have definitive answers. They're asymptotes we approach but never reach. And so we will always, in some sense, not know, and thus always be reaching, always growing. This endless pursuit is a beautiful thing. It means we are participants in a cosmic story of discovery, not just passive beings. The universe is not a static riddle to solve and be done with. It's a living conversation. Today's unknown will be tomorrow's known, and tomorrow's known will open up another unknown beyond. We stand on a threshold at all times. Behind us is knowledge hard won. Before us, the ocean of mystery. And isn't that what makes life and the cosmos endlessly fascinating? If the universe were small and simple enough for us to easily grasp in totality, it might lose some majesty. Its very unfathomability is part of its grandeur. The cathedral of stars overhead, the equations that describe them, and the equations yet to be written all form a grand, evolving tapestry. We humans are but a tiny thread in that tapestry, yet we can observe the whole pattern and add our own embroidery. Our scientific instruments are like extensions of our senses, giving the universe new ways to look at itself. Our poems, paintings, and music about the stars are the universe expressing beauty through us. We often personify the cosmos in our musings, calling her Mother Nature or envisioning gods in the sky, because deep down we feel that intimate connection, that we and it are one. And indeed, we are not separate from the universe. We are the universe, in the form of conscious living matter. Thus, the questions we ask the universe, we are in a way asking ourselves. And when we find an answer, we are the universe knowing itself a little better. Perhaps that is a kind of purpose we can latch onto, to be the mind of the universe, ever awakening further. If star systems are its body, perhaps civilizations are its mind, flickering on and off in the vast epochs, maybe one day linking up if interstellar travel or communication becomes possible, forming a network of cosmic awareness. Or maybe each remains an isolated island of thought. Either way, in us, the cosmic ocean has evolved eyes and brains that can map its shores and begin to chart its depths. The journey of not knowing to knowing, and then finding even more not knowing, is likely endless. And that is good. It means our descendants,
be they human or augmented or AI or something beyond, will always have new frontiers. Just as we looked at moons and said, "We'll go there," and did, they might look at other stars or dimensions or layers of reality and find ways to reach or comprehend them. Each answer: the moon is barren, Mars had water, black holes exist, spurs new questions. Could life endure on Europa? Could we terraform Mars? Can we travel through a wormhole? The quest fuels itself. Standing under the cosmic sky, we may feel small, but we are also giant in what we carry. The spark of curiosity, the flame of consciousness. The distances are huge, the mass is immense, the energy is unfathomable. Yet none of those physical things inherently produce meaning. A star doesn't seek meaning, a galaxy doesn't appreciate beauty, but we do. We create meaning by examining the cosmos and by simply living and loving within it. Our unknowing and desire to know give the universe meaning, as much as our capacity for joy and love do. In the stillness of a clear night, if you listen closely, you might imagine you hear the stars whisper. Of course, space is airless and there is no real sound. But there is a metaphorical voice, the voice of wonder that arises in your own mind as you behold the stars. That voice quietly says, "There is more, so much more." It invites you to ponder, to go further than those who came before, even if just in thought. It's the same voice that led ancient people to map constellations, that led Copernicus to propose the Earth moves around the sun, that led Einstein to envision riding on a beam of light. It's the cosmos, through the medium of human imagination, urging itself on to greater self-understanding. We do not know if we will ever find all the answers. Probably we won't, because each answer breeds new questions in an endless cycle. But that is the brilliance of it. We are alive in an epoch where mysteries abound, and likely every epoch will be such an epoch. We get to be explorers of the grandest kind. Whether we sail actual ships across space or ships of thought across higher dimensions, we are adventurers. Not knowing is the call to adventure. Curiosity is our compass. Each piece of knowledge hard won is a treasure we carry, but the treasure map always extends further. To be alive is to stand on that shoreline between known and unknown and feel the enticing breeze of mystery. It reminds us that we are part of something far larger than ourselves, and yet we belong. We belong in this universe as naturally as photons and quarks and nebulae. We fit because we evolved here and of it. The atoms in our bodies were forged in stars. When we die, those atoms will return to the Earth, perhaps one day to new living beings, or drift into space to join a new star. We are a transient pattern in a much larger flow, but while the pattern holds, we have the privilege of witnessing and wondering. In that sense, our not knowing is even comforting. It guarantees that the tapestry of existence is rich beyond measure. It means there will always be more to learn, more to experience. The cosmos will never run out of surprise and majesty. We humans sometimes fear the unknown, especially on the personal scale. The unknown future, the unknown outcomes of our choices. But we also thrive on the unknown, turning it into the known bit by bit. The key is to accept that uncertainty is fundamental to life and even to the universe. We will never have absolute certainty about everything, and that's okay. That leaves room for faith, for hope, for creativity. It leaves room for us to make choices. If everything were predetermined and fully known, existence would be like reading a book with no alternate endings, interesting perhaps, but static. With uncertainties, we write our own pages as we go. The great cosmic questions, then, are both scientific and existential. What is the universe? How does it work? Blends into, what does it mean for us? What should we do? There is no single correct answer to that latter part that science can give. But perhaps the very act of seeking answers is part of the meaning. Perhaps the growth of knowledge and consciousness
is one of the universe's purposes, if such a word can be used. We often imbue purpose in things that might inherently have none, but maybe that's our role, to create purpose. If the universe was initially without meaning, we give it meaning by caring, by exploring, by marveling. And oh, how marvelous it is! This strange existence, where a primate brain can comprehend the birth of galaxies and the death of stars, where mathematics scribbled on paper can predict black holes, and then the sky shows they're real, where we can read the genetic code that links us to every creature on Earth, and yet still scratch our heads about what consciousness is, or how quantum entanglement actually operates. We solve pieces of the puzzle only to find new pieces beyond the edge. It's like an infinite game, and perhaps that is the secret. Life is an infinite game, where the goal is not to win. You can't, since there's no finish, but to keep playing, to keep the game going. In this game, every new insight is a level up, every new mystery a new quest. Eventually, billions of years from now, our sun will swell into a red giant and scorch the Earth, a reminder that even the local theatre of life has an expiration date. By then, if life from Earth is wise and ambitious, it would have spread out to other stars, preserving and expanding the chain of knowledge and being. The universe will continue to evolve. Galaxies will drift apart. Stars will exhaust their fuel. Trillions of years hence, starlight might wink out as the cosmos grows cold and dark, assuming dark energy doesn't do something even stranger like ripping space-time itself. But that is an unimaginably distant future. In the meantime, we have an abundance of time and possibilities to savor. And even in that far, cold future, perhaps the descendants of our descendants, or whatever life becomes, will have unlocked deeper truths, maybe manipulating dark matter or energy, maybe tapping zero-point vacuum energy, maybe even creating baby universes to escape into when this one grows old. We can dream far indeed. Whether those dreams come true or not, they highlight our refusal to accept limits without probing them. We always seek a way, an answer, an extension. If the universe is expanding, we figure out how to navigate it. If life is rare, we treasure it and propagate it. If knowledge is hard, we train more minds and build better tools. In the reflective silence at the end of our journey, we return to ourselves, here and now. We think of all we have pondered, a universe with billions of galaxies, mostly unknown, mysterious dark matter and dark energy, sculpting fate, black holes challenging our physics, time flowing irreversibly from an ordered dawn, quantum particles dancing an unpredictable dance, countless stars with unknown planets and maybe unknown life, our own fragile existence with a mind that defies full understanding. It's a lot to hold in one head. So we breathe and we realize it's okay not to have all the answers. It's okay, even beautiful, that there is so much we don't know. It gives us room to be curious, to be astonished, to be human. The night sky remains as it was for our ancestors, profoundly mysterious, compellingly beautiful. We have explanations for the points of light now, suns, not God's campfires or what have you. But the experience of awe is undiminished. If anything, knowing how vast and how ancient those stars are makes the night more awe-inspiring. The knowledge and the mystery together weave the full tapestry of wonder. Science and poetry meet when we confront the sublime. In that spirit, we end not with a conclusion, but with an embrace of the open questions. The universe's narrative is still being written, and we are part of the writing. Our knowledge will continue to grow, but never exhaust the mystery, and thank goodness for that. The cosmic silence is not emptiness. It is a canvas for our curiosity and imagination. The stillness is not lifeless. It is pregnant with all that we have yet to discover. And the birth of a question is perhaps the greatest gift that the darkness gives to the light of mind. We remain, as ever, small creatures with big minds,
suspended between the infinitesimal and the infinite. We seek, we find, we question again. The cosmos doesn't hand us a manifesto of meaning or a clear roadmap. It simply is. But through our not knowing and our relentless pursuit to know, we craft a meaning. In the quiet dialogue between our minds and the stars, we find meaning in the very act of seeking. And so, let us cherish the mysteries. Let us cradle our ignorance softly, not as something shameful, but as the wellspring of all fascination. When we feel that itch of the unknown, when a child asks, why, how, what's beyond, or when we ourselves stare at some deep paradox of physics and feel perplexed, let's smile. That is life, that is the universe, nudging us onward. Each "I don't know" is an invitation. As long as we accept these invitations, we are truly alive, truly participating in the cosmic story. In the vast darkness, a question was born, and from that question flowed all our science, art, and dreams. We do not know all the answers, and likely never will, but we continue, eyes open in the dark, hearts receptive to wonder. For it is in not knowing that we remain curious, and it is in being curious that we remain alive in the fullest sense. The universe, speaking through silence, asks us questions in the language of awe and mystery. Our lives are our answer, an answer expressed in exploration, in love for truth, in reverence for the unknown. In this way, to not know is not just to be alive, it is to be authentically, exuberantly alive, a participant in the grand adventure as old as time and as wide as space. So let the mysteries be, and let us embrace them. Under the silent stars, feel your heart beat with both wonder and peace. The cosmos is vast and strange, and we are an inseparable part of it. In our very inability to grasp it whole, we find our place within it, searching, discovering, and marveling. This is our endless story, the slow, poetic, immersive journey through a universe of questions. And as long as questions remain, life remains vibrant. To question is to live, and to live is to bask in the unknown, even as we reach for understanding. Indeed, to not know is to be alive.